And I'm just curious, just by a raise of hands, who has not, let's just do it that way, who hasn't already taken the ADX? I'm just trying to get an idea here. Who hasn't? Okay, good. I think that's kind of like a requirement now. Got to have that done if you want to go to that in person. So good. If you can get that out of the way, you're in good shape. So, all right, you guys. Well, I think we're going to get started. Let me just double check our numbers here. We got 22 on. Let's see. Yeah, we're going to probably get started. That's about what we had yesterday. So, all right. Well, again, yeah, welcome to class. This is week 4, day 4. So just knocking them out of the park, right? Getting ready for the preparation to go into the in-person portion, which everybody should be excited about. This is not the exciting part of your class or your journey to get your certificate. This is just those check boxes, right? You're just putting a check in the box and moving on. You really learn a ton come week 7 and 8 in person, where all of this starts coming together. So again, please look forward to that. Just push through these next few weeks and look forward to being in St. George. Good weather, good people. You guys are all going to really enjoy it. I know. Well, today's agenda, we've got a quick review of the material that we covered yesterday. And this review, again, is going to pretty much hone in on everything that you guys really need to know and take away from yesterday's material. A lot of stuff was thrown at you. It'd be great if everything stuck, but as we mentioned yesterday, it's not going to, and that's okay. But between my little reviews that I do and the reviews that you'll do with another instructor come the end of the week, and as you keep building on these concepts, a lot of this stuff is going to start sticking. You're going to start remembering and recalling a lot of the material that we're talking about, especially once you start applying it. So again, please use this time during our quick review to ask questions if something doesn't make sense regarding a topic that we're going to cover. Okay. Once we do our review from yesterday's material, today's the day that we get to dive in a little deeper and talk about the VFR sectional, which is that colored map, right, that pilots use when they're flying visually, which we don't use a whole lot, but we're going to look at it for just a second. And then we're also going to discuss some specifics regarding the IFR en route charts. And can somebody tell me what IFR, what that acronym stands for? Just as a reminder, let's go with is it, oh man, I'm going to butcher this, man. Is it Orion?
It is instrument flight rules.
Instrument flight rules. Perfect. Okay. So again, that is what we're going to want to focus on. And that's what we're going to try to get you guys familiar with is the IFR en route charts. Okay. And that's the chart that has all those lines everywhere showing those freeways in the skies. There are 2 charts that we need to become familiar with. It's the low chart and the high chart. So it's just based on different altitudes. And we're going to, again, break those down and help you guys become familiar with that today. We'll look at SkyVector. So those of you who don't know what SkyVector is, again, that is the online website that allows us to do our flight planning on, right? We can build a route from point A to point B. I don't expect you guys to know how to use SkyVector today. I'm just going to use it so that I can show you around and point out different symbols and altitudes and different things on the aeronautical chart. Okay, next week I think is where you guys begin using SkyVector with an instructor, and that whole class is geared towards basically introducing you to SkyVector, and then you guys begin using it with the assistance of an instructor next week. And then the last thing we'll talk about today is the approach plates, the instrument approach plates, or those papers that pilots will use to know what courses to fly, what speeds to maintain, what altitudes to maintain to stay clear of obstacles, and then ultimately guide themselves down to the runway or airport environment. Okay, and that is where you, as a dispatcher on those instrument approach plates, that's where you're going to locate what the minimums are for an airport. And you need that. You have to determine what the minimums are so that you can ask yourself that question during the process of flight planning. Am I legal to go? And when you ask yourself if am I legal to go for this flight, you're going to be looking at visibility in the TAF, in the forecast. And you've got to be able to compare what that visibility is at your estimated time of arrival to what the minimums are displayed on that approach plate to make that decision. Am I legal to go? Okay, and that's a process you're going to do over and over and over again. It's going to become really repetitive until it becomes second nature. Right now, it definitely isn't, but it's a skill that we're going to help you learn and become familiar with by the end of your 8 weeks here. And it all begins with knowing, what is this instrument approach plate? What am I looking at? Okay, where are the minimums? And that's what we're going to kind of break down for you later on today. So before we get started on this review, do I have any questions from any of you? Anything at all? No? Okay. Noah, I just noticed your hockey stick above your door. I love it. Yeah, I'm an ice hockey guy. I played hockey a lot. I was an instructor, a coach. Played a lot of adult league and all through high school. So that's awesome. Do you play?
Yeah. No, I wish, but
Oh man,
I'm a big Utah Mammoth fan, and that was part of their sale at the end of the inaugural season. So it's one of the players' sticks that they used during a game.
Is it really?
Yeah.
Oh, lucky. That's awesome. That's pretty cool. Yeah, I'm a Mammoth fan now myself. You know, I moved out of Utah, I grew up there and everything. No hockey team while I was growing up, other than the Grizz. And it's like, oh man, we got an NHL team now. So naturally, they're my team. So that's pretty cool.
If it makes you feel better.
What was that?
I was going to say, if it makes you feel better, I still don't go much because tickets are way too expensive.
I know. I've been wanting to go because I live in Oklahoma. I've been wanting to go see the Stars play the Mammoth in Dallas. And man, the nosebleeds are like $120. So
it's crazy.
I'll make it out there eventually.
Yeah.
So, all right, you guys. Well, during this review, this is not like a formal review, right? Just you guys you can raise your hand if you want. I prefer you not do that. Just unmute and just say it if you don't mind. Okay. Again, if you don't understand something that I'm asking after we've answered it, stop me. Let's talk about it and let's review it. Okay. And if you decide that that's not what you want to do and you want to wait till the very end of class to go deeper into it, I'm fine with that too. But remember that if you have the question, there may be somebody else who has the same question in class. All right, number 1. What do we call the line where true north and magnetic north are equal, where there's no difference between the two?
Agonic.
The agonic line. Okay, perfect. The agonic line. Number 2, what are the lines called that show the different magnetic variations? Like the 9 east, it could be 9 west. What do we call those lines that we saw on the aeronautical chart? What was that?
The azimuth. I don't really know how to say it.
It's not the azimuth. The azimuth we'll talk about here in just a minute.
Okay.
Isogonic.
I think Trevor said it. Or was it Brian?
Yeah, I think it's both of us, but yeah, isogonic.
Yes, the isogonic line. So again, the isogonic line is going to be either a green thin line that runs through, I know I'll show that to you later, that runs through your chart, and it'll have a degree value with either E or W listed, okay, on that IFR en route chart. And on the VFR charts, they're a dashed magenta line. And they just kind of run straight through the map, the chart. Okay, that's the isogonic line, which helps you understand the magnetic variation between true north and magnetic north. And we'll look at that here in a little bit again. Okay. Here's a true or false question for you. So true or false, a line or a course that is drawn on a physical aeronautical chart is considered to be a true course. A line or course drawn on a physical aeronautical chart is considered to be a true course.
True.
Okay.
Trevor said it. He said true. Trevor, why is that true? Why is that a true statement?
Because those lines are aligned with true north.
Exactly. Yeah. The maps that are created, right? They're overlaid on top of the latitude and longitude lines that are oriented with true north. So naturally, if your map is oriented in such a way that it's oriented with true north, any line or course that you draw on that map is going to be a true value. Brian.
So the exception to that though would be like those radial values that are displayed like around a VOR. Is that right? Those are based on magnetic, right?
Yep, those are all magnetic. Yep, because you can even see, and we'll look at it again later today, but that VOR compass, everything's kind of tilted a little bit. And it's because it's already taking into account that it needs to be in relation to magnetic north and not true north. Because the magnetic values are what a pilot wants to see, right? That's useful to them. And that's the whole reason why those freeways in the skies are there, is for a pilot to use that to navigate. So they've already said, okay, well, we're using a map that is oriented to true north. Can't help that, right? That's just how it is. But what we can help is we can ensure that those other items on there, like you said, Brian, that VOR is already oriented to magnetic north. Yes. And we'll see that again today. Number 4, what is the difference between a true course and a true heading? So you may have a certain course that you're flying on, right? But what's the difference between a true course and a true heading? And you know what? Let's just even simplify this more. What's the difference between a course and a heading? Answer that one.
Course is
Course
corrected
is-
for wind.
Yeah.
Go ahead, Chris.
I think we said it at the same time. A course is corrected for wind.
Exactly. Yeah, you can have a course, right, going from A to B, but that doesn't necessarily mean that you're heading, right, or the nose of the aircraft is going to be pointing in that same direction. Because of wind, you may have a different heading. So just kind of keep that in mind, especially as you're going through these flight plans later on. You're going to figure out a course, but then you're also going to have to take into account the winds aloft, the winds along that route, and you're going to have to do what's called a wind correction angle to determine, in order for me to stay on this course that I've determined and this expected wind, where is my nose needing to be pointed? In what direction? And so they're going to show you that again in the in-person, that here's your course, but you're also going to have this heading that could be different because of wind. And we kind of showed you that in that slide yesterday. Kind of think about like rowing a boat, right? You kind of seen those pictures. If you're trying to row a boat from one end of the stream to the next, and you've got rushing water, right? You may have to row upstream there a little bit to kind of stay going straight. It's the same thing with the aircraft. All right. The next question: how do we convert a heading from true to mag? There's something that we have to remember. Again, this is not something you'll probably do a whole lot because you're going to be using a lot of automation. But whenever we have a true value and we want to make it magnetic, what do we do? What do we have to? What's the
The-
process?
East is least and west is best. So for the east, you have to subtract whatever value shows. So if it says like 9 east or 10 east, you would subtract 10 or 9. And then for the west, you would add.
Yes, and then you add for the west, right? Exactly. Yeah. So yeah, you'll come up with that true course. And if you need it to be a magnetic course, you got to go find that magnetic variation, the number of degrees that is different between true and magnetic. And then you're able to add or subtract that value. Yesterday, our example was 9 east in one of the slides. So that would tell me that I need, because of the east is least. That means I need to then subtract those 9 degrees from whatever my true course is. And then like you mentioned, again, if it were a 9W, that means east is least, west is best. And therefore I would have to add those 9 degrees. Okay. And I have an example to show you that within SkyVector today. That again, whatever line I draw is true, but then it automatically converts it to magnetic for you. I'm going to show that to you, and you're going to actually see it today. Okay. What are some differences between? Oh, you know what? We'll wait. That one we're going to do today. Somebody name at least 3 different types of ground-based navigation systems. Navigation systems that are on the ground. Okay, not satellite based. But what are some 3 facility
DME,
navigation aids?
NDB.
Yep, we got NDB and I think you said VOR, right?
Yes.
Okay, perfect. Thank you. VOR, NDB, anybody else?
DME.
DME, yeah, that would be another one. Yep, that's true. There's 2 other ones that we talked about yesterday as well that do provide guidance, navigational guidance to a pilot. And your hint is going to be it's related to some type of an approach.
You're at the guide slope and the
Yep.
Wait.
Yes.
Locator?
Localizer.
Localizer.
Yep.
Yeah.
You got it. No, yeah. So the glide slope and the localizer are other facilities on the ground that provide that guidance. So in addition to that question, and then with that answer, Brian, you can answer if you'd like, but somebody else can answer. It doesn't matter. What kind of guidance is the aircraft or the pilot getting when they have a glide slope and a localizer?
The precision approach.
Yeah, it's a precision approach, right? So the glide slope is providing that vertical guidance. That localizer is providing the lateral horizontal guidance. Okay. All right. What are the 3 different types of VORs? So we talked about 3 different variances yesterday of VORs. Somebody name them off for us.
VOR, then you have VOR, DME, and Vortec.
Perfect. Was that Michelle? I think.
Yes.
Yep. Thank you. That's perfect. Okay, did everybody get that? That is important. The VOR has 3 different variances: the VOR, VOR DME, and the Vortec. Now, naturally, the next question is going to be, what does the pilot get out of each of those? Okay, they each have certain things that they give a pilot for navigation. Let's start with the VOR. What do you get out of a VOR?
360 degrees worth of radials.
Perfect. Anything else on that? No, that's it. Okay, there's nothing else. I wish there were more, right? But there's not. Not until you get to the VOR DME. Somebody remind me what the DME acronym stands for?
Distant measuring
Distance
equipment. Oh, that's good.
Go ahead, Trevor. Go ahead, Area.
Go ahead.
Yep,
Distance measuring equipment.
Yep, distance measuring equipment. Perfect. Thank you. So what do we get out of a VOR DME? Let's go with Joseph. Were you going to answer earlier?
Yeah, so you'll get like your distance from the VOR broadcaster as well as the radials.
Yep. In addition to having all of those 360-degree radials, we also have that distance measuring equipment. So the benefit of that is that now, not only are we on a radial, but we can also determine where we're at along that radial. That's really helpful. Does anybody remember what other term is used to describe those different radials? So we said they're called radials, but there's also another name for them.
Azimuth.
Yes, azimuth. Okay, you may hear that or see that, I don't know, maybe on a test or something, I don't know, but I heard it's out there somewhere. So, okay, the last version or the last variant of a VOR is a VORTAC. So walk me through that one a little bit. What are we getting out of a VORTAC? Or what is it? Let's start with this question. What is a VORTAC comprised of? Is it, how do you pronounce your name? Is it Siwar? I'm sorry, I don't want to keep mispronouncing it.
Yes, it's Siwar.
Siwar, okay. Yeah, go ahead.
So the VORTAC is a VOR and we tack it.
Mhm.
And from the VOR, we take the 360-degree radial. Basic. And from the TACAN, we take the DME because we cannot read the frequency of the TACAN. So aircraft cannot read that. Our aircraft cannot read that. It's for the
Yep.
military, I guess.
Yeah, it's working off of a different frequency that
Yes.
Chris's plane would be able to pick up, but
But we
not us
use the
civilians.
DME from it.
Yeah, but we do have the DME. That's where the DME portion of the information is coming from, right? It's coming from that TACAN. So again, we know that the VOR is still sending out those 360-degree radials. And we also have DME because of that TACAN portion that is co-located with it. So the reason why this is so important, you guys, is because as a dispatcher, you will see from time to time a NOTAM that says that the DME portion of this VOR is out of service for a VOR DME. Great. Well, that's pretty clear, right? We know that in that instance, that VOR does not have DME capability. There's the other aspect of it where you'll see a NOTAM for a VORTAC, and the NOTAM will say that the TACAN is out of service. If you see a NOTAM like that, which you will, that means that you still have 360 degrees worth of radials, but you don't have the DME capability anymore. So it's important to understand the anatomy of these VORs so that when you're looking at NOTAMs, you're able to clearly identify what limitations are placed on that facility or that NAVAID now that the NOTAM is out. Brian.
How would you know about those NOTAMs for the VORs? Would they just come from like the nearest airports as part of their NOTAMs, or how else would you find that out?
Yeah, your company's you're going to have a NOTAM package given to you, and it's going to have a compilation of all the NOTAMs that you need from your destination to your from your point A, depending on wherever that's at, to point B. So you're going to have a whole packet given to you that you get to look through, and it's going to include those NAVAIDs or those VORs and different like localizers that are going to be used along your flight.
So are those published by like ATC or
Yes, yeah, the FAA publishes those. Yeah, it's not necessarily ATC. They communicate with a NOTAM office, and part of that NOTAM office is actually here in Oklahoma City. They call up and say, "Hey, this is out," and they'll type out a NOTAM, and it'll get sent out into the system for the public to view. Yep. All right, so those are the 3 different variances of a VOR. Somebody remind me, what is a SID? We'll go with the acronym first. A SID. This takes us towards the end of our day together yesterday. Let's go with CWAR.
Standard instrument departure.
Standard
SFP
instrument-
route for pre-planned route for departure. Yeah.
Mhm. Yeah, and what does this pre-planned departure do? I mean, it kind of, yeah, it's a departure that's been developed, right, and agreed on with the air traffic controllers, and the pilots agree to fly it. What does that ultimately do for the both the controllers and the pilot? Brett.
It minimizes ATC workload and streamlines departures out of congested terminal areas.
Absolutely, because they know what courses they're going to fly, they know what speeds to maintain and altitudes to maintain, to not only stay clear of obstacles, right, but to stay clear of other aircraft, and the air traffic controllers know where they're going to be. So yes, it's to help reduce the workload of our pilots and our controllers. A STAR, right? A STAR is a standard terminal arrival route. It has the same purpose, right? But instead of helping get aircraft out of an area, we're trying to bring aircraft into an area. Now, there's one thing that we didn't have enough time yesterday to talk about, and I'm going to try to bring that up right now. And again, I'm not even going to put this in presentation mode. Okay, this is going to be quick. I just want to show you. Okay, I want to show you really quick on an arrival, or on any chart. Okay, if you ever see, all right, hopefully you guys can see this. It says STAR over here on the right-hand side. We good? Looks like it's presenting. Okay. All right, so these big black bold lines here are the actual routes that the aircraft is going to be flying. All right. You have these VORs out here, however, that have these thin gray lines. I'll move this over a little bit. Okay, these thin gray lines over here. These are not routes to be flown. Rather, they are, if you remember from yesterday, we talked about crossing radials, right? Where you can use 2 VORs, one VOR with the radial that the aircraft is flying on, and then another radial coming from a different NavAid or a different VOR to help identify a fix or a point in space. So in this instance, my aircraft is right here where my green arrow is pointing, and we're flying from top to bottom on the page. And my pilot is going to be flying using a VOR that's coming from up here, okay? They're flying away from it, but this is a radial. They're going to be flying on that radial, but they're also going to tune in, if they need to this one, PCU, on that frequency, and this radial, the 253 radial, is going to assist my pilot in determining when they get to this fix right here, oscillity. Okay. Now, the other way they could identify this point is just using DME, right? They're on that radial, they're flying on that radial away from the NavAid, and when it says DME of 50, they know that they've reached this point. That's the easiest. But not all aircraft, especially older, less equipped aircraft, sometimes don't have DME. So they have to use these reference radials, okay, or crossing radials to help identify and to X marks the spot on a course that they are flying on. So again, just keep in mind that when you're looking at these arrivals and departures, if you see these thin gray lines, these are not areas that the pilot's going to fly on. They're showing the radials being used to help identify different points on the routes that the pilots will be flying on. Okay. So that's something we didn't get into yesterday, and I wanted to make sure you guys had the opportunity to see that. All right. Really quick, what are the different types of NavAid service volumes? So we already talked about the 3 different types of VORs, but we also talked about how each of those VORs can be classified and given an advertised strength. They're the legacy version and the new version. Let's have somebody list off the legacy service volume types.
Terminal, low, and high.
Perfect. And can I have somebody else give me the maximum range associated with the terminal, low, and high?
Terminal's good out to 25 nautical miles. The low's good to 40. And the high is good to a max of 130.
Exactly. And that's really, as a dispatcher, that's what we want you to know. Okay, for that. And now let's have the same thing done for the new classification of VOR service volumes. Anybody remember those? So you guys named off all the legacy ones, terminal, low, and high. Let's go with CWAR.
It's the same, right? The low and high is still the 40 and 130.
On the new, it's actually VOR low, VL, and it's now increased to 70 nautical miles.
Oh yeah, it's the 70. Yeah.
And then the VOR high, or the VH, that's still good up to 130 nautical miles. But just remember, you guys are learning this while the FAA is transitioning from a legacy VOR service volume classification to a newer, more modified, more modern classification naming. So you unfortunately have to learn both until everything has been transitioned over to the new service volume. Okay. And does anybody remember what the 2 GPS augmentation systems are that we talked about yesterday? Those augmentation systems that help improve the reliability of the GPS information that the aircraft is receiving. There's, again, two types. So we got CWAR, let's see who else can answer this one. Who else do I have? Let's go with Alan.
We have RAIM and WAS.
RAIM and WAS, okay? You have the Receiver Autonomous Integrity Monitoring, RAIM. That's where it uses all those different satellites, and it's able to detect satellites that are not behaving or positioned in such a way that's going to provide a reliable signal. So it'll kick one out and replace it with a good satellite. It'll also notify the pilot when the GPS signals are not reliable so that they can revert back to ground-based navigation. And give me a second, you guys. My power, I forgot to plug it in. Don't want to drop the connection here. I apologize. There we go. Yeah, and then you have the other one, Alan, you said WAS, right? The Wide Area Augmentation System. So that is where the aircraft's WAS receiver is able to receive very quickly and often calibrated and recalculated GPS signals so that it's constantly receiving the most accurate GPS information that it possibly can. And that WAS receiver is the newer augmentation system out there that is allowing us to develop and create very precise instrument approaches into areas such as Alaska, in areas where it's not really feasible geographically nor financially to install equipment such as the ILS system, because they just don't have the funds for it, or the airport's just positioned in a way that, you know, one of those systems is not really suitable for that area, that terrain. So we can actually still achieve just as precise of an approach into some of these remote Alaska airports because of WAS, because of these reliable GPS signals. We can now guide an aircraft laterally, but also vertically, very precisely, just like we can with these other components, like what we learned about yesterday with the glide slope and the localizer, the ILS system. Okay. All right. So really that material right there, you guys, is what we need you to take away from yesterday's class. It's, you know, again, we're trying to build on these concepts. Are there any questions as of right now with what we've covered with those items there? Okay. All right, for the next 30 minutes, we're going to kind of just dive in really quick to a PowerPoint. Give me a minute to get that set up. And here at the bottom of the hour, we will make sure to take our break. This PowerPoint's not very long. It's not too terribly long. So we'll get it started here. Move you guys over, shift things around. All right. So now we're looking at the PowerPoint for the VFR and the IFR en route charts. So we're not going to spend a ton of time on this, but we are going to start with those VFR charts. And somebody remind me with what you know up to this point, what kind of things do we see? And I'm going to go back. What kind of things do we see on a VFR chart? You guys remember? I know some of the pilots out there will know. And a hint, it stands for visual flight rules, right? It's a visual flight rule chart. You're using your eyeballs out the window, right, to kind of navigate from point A to point B. So what kind of things are on this chart?
More terrain and just, you know, just geographical landmarks and things like that.
Perfect. Yeah, you got your airports, yeah, your terrain, you got bodies of water, towers, right? We talked about that yesterday, railroad tracks, interstates. And that's because, again, this is being used by people who are flying visually, and they're not fully relying on their instruments to get from point A to point B and to navigate throughout the NAS. And again, we will not be using this, but it is important to know what it is, because you're going to come across it when you are working in SkyVector or other programs that are helping you with your flight planning. The chart that you will use, and you do need to become familiar with, is the IFR en route chart. The IFR en route charts have two main charts, okay? And there's an en route low, which is what we're looking at here, and there's also an en route high. And it all has to do with the altitude that you're working in. So the IFR en route low is going to be for those flights below 18,000 feet down to 1,200 feet AGL. Okay? And all of these different freeways in the skies here that are in black, are being connected by different VORs. And as we mentioned yesterday, what VOR variant is used the most to create the freeways in the skies throughout the NAS, or the National Airspace System? Does anybody remember?
Vortec.
It's a Vortec, okay? The Vortec is the one that is used the most to create these freeways in the skies. And in this class, these low charts are sometimes used in our flight planning. You'll also notice that the freeways in the skies here on this chart, the ones that are using ground-based nav aids to create the routes, are listed in black, and they have a V on the low chart. This is called a Victor Airway. We also have these blue routes here, but instead of being created based on ground-based nav aids, these blue routes are the GPS routes. And they're listed with a T, a Tango route. Now let's look at the high chart. The high chart pretty much looks the same way, but you're going to use this chart, the high, whenever you're dealing with flights that are at flight level 180 or 18,000 feet to flight level 450. This is the one that you're going to be using the majority of the time in this class. And if we zoom in a little bit, all of those black lines, again, are representing routes that are using and are dependent on those ground-based VORs, okay, that radio frequencies. It too has routes in blue, and those are called the Q routes, and that again is our GPS-dependent routes. And if you look here, this J on the black line, that's the jet route, the jet airway there. That's what we call them on the high chart. Okay, so the black is showing the VOR dependent freeways in the skies, and the blue lines again are the GPS equivalent. There's still a freeway in the sky, but instead of tuning and having to tune in and be dependent on a radio signal, it's using GPS to navigate through the skies. So this is a new topic right here that some of you may or may not know, but when you're trying to determine your altitude that you're going to file with ATC for your flight, it's all dependent on the direction of the flight. So if you have an overall magnetic course from your origin to your destination of 0 degrees to 179 degrees, you're going to file an odd 1,000-foot altitude. And I'm going to show you what that looks like here in a minute. And then if you have a magnetic course between 180 and 359 degrees, you're going to file an even 1,000-foot altitude. And here's an example of that. We have a flight from Seattle all the way out to Atlanta. And it looks like the overall track for this flight is 116 degrees. Okay, which puts us over here in the odd flight level. And wouldn't you know, here on Flight Radar 24, look at what altitude the aircraft is at a little over half of the way to Atlanta. It's at an odd flight level of 33,000 feet. If this were a flight from Atlanta back to Seattle, I would expect to see this altitude at an even flight level, say 340, flight level 360, and so on. It would be an even altitude. Any questions with that topic? Because that is new for today. So in class, you're going to determine your route, you're going to look at the overall course and you're going to ask yourself, okay, does this fall within the 0 to 179 or the 180 to 359? And then you can make your decision off of that, whether you need to file an odd or an even flight level with ATC. Brian.
Does that apply for lower altitudes as well?
Yes, as long as you're filing IFR, this is what you would need to follow. Yes. Yep. And just like it mentioned down here, see how these examples aren't as extreme, right? So, yes. And it's magnetic tracks above 3000 AGL, which don't think too much about it. With what you guys are doing, you're always going to be doing this odd or even determination for your flights. Yep. Anybody else with any questions? Yeah, Rebecca, with what Rebecca is typing in the chat, there are different ways of remembering this. Some people say that Easterners are odd, but Westerners are even odder or something like that. So there's different ways of trying to remember this. I've heard odd Sweven is one way. I personally like the East is odd, but West is even odder. So odd Sweven, if you think of a circle, but yeah. Okay. So this is kind of fun. So the next time you guys get on a flight, you know, and you're coming, let's say San Francisco to St. George, you're going to be on a most likely an odd flight level. So okay. Some things to look at and to watch out for, these little dispatch flight planning details. All right, so today, once we're done with this boring PowerPoint, we're going to be looking at SkyVector. We're going to go in there and we're going to actually look and poke around in the low and high en route charts, and you're going to see a bunch of different symbols, right? And a lot of this stuff, it's going to take time to learn. You're not going to learn everything right now. I mean, I do this for work, and I still have to go and look at these different legends that are available to us because there are just so many symbols. It takes a long time to learn all of them. So I do have within our PowerPoint different links that you guys can access, both for Jeppesen published symbols and charts, and also the aeronautical chart user guide from the FAA. Both of them are colored publications with, it's basically just a huge PDF file that's used as a legend so that you can go through here and go, what does this symbol mean again? Ah, that's what that is. Okay, so that is available to you. And it kind of looks like this, just for an example. Here's a VOR symbol, VOR DME, a TACAN. The box means DME. Okay, so it'll kind of tell you what this is. Sometimes when you're looking at these different aeronautical charts, your NAVAID is going to be filled in completely black. And that means that it is a compulsory reporting point. Any of my pilots out there want to give a definition as to what a compulsory reporting point means? If you see one of these, what do you think you're going to have to do with ATC? How about that? Anybody know?
You have to
Typically report your position, time, and altitude over that position, and usually you got to report your next point, time, estimated time at next point.
And the reason for that, you guys, the reason why they're having you report your position, your next point that you're flying to, is because there's a lack of radar coverage maybe in that area. And so they want you to check in with ATC over these points. So we call those compulsory reporting points. And those are identified on our charts with a filled in solid NAVAID symbol. And this could even be for a fix. Remember the triangle? that could be filled in black as well. And if you cross over that point, they want you to report that information to them. This is important for you as a dispatcher. If you ever see a freeway in the sky, like a Victor Airway, this Victor 12 here, and a gray squiggly line just through it, that means that ATC does not want you to file that airway in your flight plan. You're not allowed. It's unusable. And there can be a number of different reasons as to why, but please, during the course and during your practical, don't plan a flight through an airway that has this gray squiggly line. Okay, it's an unusable route. You can also come in here and see symbols that we've already talked about, like this little D with a number in it. That's telling you what the DME distance is to a specific fix. If we look here, this is a NavAid, a VOR DME, and a route in black, that's the freeway in the sky, with these different fixes here. Well, this is telling me that this fix is 5 DME, and then from this fix to the next fix, it would be 10 DME. And if I were flying from the NavAid all the way to this last point, well, look at what it's done. It's added up what that DME distance would be over those different segments to give you a total DME distance to this fix from the DME source. Any questions on that? Make sense? Okay. So here are some depictions. Oh, yeah, go ahead.
I'm sorry.
You're fine.
Does this apply to both the FAA supplied charts and the Jeffersons? Is it the same for both? Okay.
Yeah.
And I guess on that, should we be spending the majority of our time looking at the Jefferson ones? Because it seems like that, you know, I don't know. I've heard Jefferson is what almost everybody uses, right?
It is, and we are going to try, when you get into the in-person class portion, they have packets of all Jeppesen material. However, for your flight planning, I've heard that they still use SkyVector, which SkyVector is using government issued charts. Okay, so you honestly, you got to learn both, but you're right. When you get into the airline industry, they pay for a Jeppesen subscription, and that is honestly what they use. But if you can understand a government chart and you understand the theory behind it, you can pick up a Jeppesen chart and be just fine. So, but for right now, you kind of have to work with what you have. If somebody has the money right now to go and buy a Jeppesen subscription, I wish I had your job and your money. Because it is expensive. So we kind of have to work with what we've got. And unfortunately, the government charts are free. So you will see a lot of that material being presented in this course for that reason.
Okay, gotcha. Thanks.
But great question, Brian. Thank you. Here's again just fixes that are both compulsory reporting and non-compulsory reporting. Okay, the very high frequency type fixes and other fixes here that use a lower frequency, but you don't really need to get into that. I just want you to know that the triangles represent a fix using radio facilities like a VOR to identify them. And then if we come over here, this is a GPS waypoint, both a compulsory reporting point and non-compulsory reporting point waypoints. They have a little star symbol. Those are the points, just like a triangle, a fix, right? But we call them waypoints when the GPS is used to identify a point in space. And this is the symbol they use. And we'll look at those, couple of those today in just a minute. All right, this is really important. This is why I wanted you guys to watch that video. Hopefully you guys were able to watch the video. If not, that's fine. You're still going to get the same information here, but it's always nice to hear it 2, 3, 4, or 5 times, right? Especially when things can get a little complex. But there again are a lot of altitudes on these aeronautical charts. And not all of them are, critical in needing to know immediately, like today, for your dispatch experience. It's with time, so you'll learn all that. But right now, we want to focus on the altitudes that you do need to be familiar with starting out. So give me the next, I've got 5 slides to get through, and then we'll go on our break. So the first important altitude that you're going to notice on these IFR en route charts is called the MEA. It's this one right here. So here's our airway, the Victor 55 airway. That number at the top is my minimum en route altitude. And this is going to be the lowest published altitude between radio fixes that will ensure both obstacle clearance, so I won't hit anything while I'm on this route, and it also ensures that I will have the ability to pick up the signal coming from the VOR to help me navigate throughout this airway. So again, the minimum en route altitude makes sure that I don't hit obstacles, and it also makes sure that I'm high enough so that I can pick up the signal from the VOR to continue navigating on. And just a little side note here, for the obstruction clearance, the pilots are guaranteed at least 1,000 feet of clearance over an obstacle in non-mountainous terrain. And this altitude here in a mountainous area will provide at least 2,000 feet of obstacle clearance. Okay, so it keeps them really safe and away from those obstacles as long as they can maintain an altitude at or above that MEA. Everybody good on this one? Minimum en route altitude? Okay. The next one below the MEA, with this little star here, this asterisk sign, okay, this is going to be your minimum obstacle clearance, or your MOCA. This altitude that we're pointing at here at the blue arrow, this is going to make sure that you remain clear of obstacles, okay? We always want to keep them clear of obstacles, but it's only going to ensure that you have sufficient navade reception as long as you are within 22 nautical miles of that navade providing that course. Okay, so again, the MOCA, minimum obstacle clearance, always make sure that you are clear of obstacles for that entire route, that airway. But it will only guarantee sufficient navade reception as long as you are within 22 nautical miles of the navade that's helping define that airway. And here again, you have the same kind of obstacle clearance for non-mountainous and mountainous terrain. Not too worried about that though, you guys. All right, the next one. You're going to see this little flag out there with an R on it. Okay, this is your minimum reception altitude. Okay, minimum reception altitude. This is going to be the lowest altitude for adequate reception from another off-route navade to identify an intersection fix. So let me explain that. Right here, we have a VOR. I'm sure it's a Vortac. Okay. And I'm flying on the 252 radial to this fix right here named Zambi. Let me zoom in a little bit. Hopefully that helps. Okay, I'm flying on the 252 radial, and I'm going to continue flying until I get to Zambi. But the only way, well, there are two ways to really identify Zambi. If my aircraft is equipped with DME, we can continue going until we get to 16 DME, the same length of that segment. But there are times where an aircraft doesn't have DME, so we have to use, like I've said before, another radial from another nav aid to provide what's called a crossing radial through the radial that we're actually flying on. Okay? The issue is that if I am not high enough while I'm flying on this radial 252, I'm not going to be high enough to receive the reception from this VOR way down here off the chart. It's the TST VOR. And the 345 radial crossing through that airway. So what it's saying is, hey, here's a reception flag telling me as a pilot that I need to be at 9,300 feet or higher in order to take advantage of using this VOR down here and this 345 radial to help me identify that fix named Zambi. Okay, if I'm below that, I run the risk of not being able to pick up TST and not being able to identify this point. If I have DME, then I don't do this, right? This is for the poor pilots. The pilots that don't have the money for the fancy equipment, right?
The ones that aren't using the Jeppesen charts.
The ones that aren't using the Jeppesen charts, exactly. So does this concept make sense, you guys, with the reception? It's telling you that you need to be at a certain altitude in order to pick up the reception of another VOR that is helping you identify a point along your route. That's the minimum reception altitude. Okay. Then you have the minimum crossing altitude. Okay. This right here is just telling me, hey, here's an X in the flag, and it wants me to cross this fix at a certain altitude on this airway, Victor 330, going eastbound. If I'm going westbound, then I don't really need to worry about it. But if I'm traveling eastbound, they want me to get to a higher altitude. So we'll leave it at that. Minimum crossing altitude, MCA. And then last but not least, you have the AROCA, the off-route obstruction altitude. And again, there are two names for the same thing, depending on if you're using government charts or Jeppesen charts. They've got to be complicated, right? So we call it the AROCA on our government charts, and the MORA, the minimum off-route altitude for the Jeppesen charts. And you'll notice when we get into SkyVector here, you're going to see these quadrants, all these squares, big giant sections, and each of these areas have a big giant number in the center of them, telling the pilots that if you're off route and you're not on one of these airways that have been flight checked, we can guarantee that you will clear obstacles by either 1,000 or 2,000 feet, depending on if you're in mountainous or non-mountainous terrain. But if you maintain 12,500 feet somewhere in this square, you are guaranteed that you will clear all obstacles. Okay, that's either the off-route obstruction clearance altitude, the AROCA, or MORA for a Jeppesen chart. All right. Any questions? What questions do you guys have for me with those important altitudes? Let me go list those off again. MEA, MOCA, MRA, MCA, the minimum crossing, and then the AROCA. Everybody good? There's a lot of altitudes, but those are the ones we want you to focus on. And honestly, those are the only ones you really need to know as a dispatcher. I really wouldn't get too carried away with too many more. Okay. Well, with that, let's be back in 10 minutes, you guys. Okay. Hands raised, cameras off, and I'll see you in 10. And again, I just added the timer at the top so you guys can see the countdown for our break, okay? Hopefully that helps. All right, guys, looks like we've reached the end of our break. We're going to continue going. We've got quite a bit to cover, a lot of good stuff to cover. So can everybody see the VFR sectional, the SkyVector screen? Are we good there? Okay. Excellent. And if you guys can, if you're back at your desk, go ahead and lower those hands. We'll get those cameras back on. Keep the FAA happy. There we go. All right. So we're going to go over again and just introduce to you guys and poke around for a bit throughout the VFR sectional, but mostly the IFR low and high in route charts. If you guys don't know what SkyVector is, if you've never heard of it before, I highly recommend that on your own time, go to skyvector.com and kind of just get a feel for what SkyVector is. I recommend going onto YouTube, getting some SkyVector tutorials so you can kind of see how it's used and the different functions that it and the capabilities that it has, so that you are prepared and ready to kind of watch your instructor, I think next Friday, go in and use this and show you around. I think it's going to be really good for you guys if you could do some of this beforehand. So I'm not here to kind of walk you through how to use SkyVector. It's mostly just a tool that I'm going to use to, again, show you around and look at different symbols and altitudes and discuss things from what we've already talked about from the previous PowerPoint. But by a raise of hands, let me see. Raise your hand if you guys feel somewhat comfortable with SkyVector, or you at least know what it is and you've seen it and you've been playing around in it for a little while here. Okay. All right. Good. Again, if not, it's free. Go ahead and use it to your advantage. It's skyvector.com. Okay. All right. Again, at the top right, you're going to see different ways to toggle back and forth from the world VFR chart and the world low or the world high. Okay. So the world VFR is just showing you the entire world's VFR sectional chart. And then this low and high over here refers to the IFR low and high charts. I'm going to go back to the VFR chart again and just show you this is the area of Oklahoma City. I can see again the different airspace classifications around these different airports. I can see the airport themselves. These little teepee symbols are obstacles. I can see different bodies of water. I can see main interstates, railroad tracks, windmills. So there's a lot here, again, that a pilot flying visually would use to help them navigate. Okay. Now, let me go over here to Lee County Regional and Gaines County. I've gone ahead and created a route really quick from point A to point B. And again, if we look at this sectional chart, or on any aeronautical chart, you're going to see the longitude line and the latitude line. Again, these are oriented with true north. So if I were doing this on paper and I drew a line with my plotter from this airport to this airport, like you see here with the magenta line, I have just created a line that has a true course. Again, if I were to do this on paper with my pencil, okay, I've created a true course. And technically, this really is a true course here digitally anyways, but it already over here has converted that true course to a magnetic course. And that's what I want to show you here, is that you guys are really lucky. Again, you're not going to have to do that conversion, but I want to show you what SkyVector is doing in the background to get to this magnetic course of 85 degrees. Because I put in my departure and destination, my points, I have a point A to point B now. I can toggle this little window here, and it will give me more information about these 2 points, including my magnetic course of 0.85 degrees. But this little value here in the parentheses, and I'm sorry I can't zoom in, it won't let me, I've tried. It says that it's a 0.91 degrees true. So again, I drew this line, and that's a 91 degrees true course. How in the world did I go from 91 degrees true to 85 degrees magnetic? Any ideas? How did we go from true to magnetic? What did SkyVector do to get to that value?
Must have interpolated the variation.
Yep, it took the variation, right? So I drew a 91 degrees true. And if we look at this dashed magenta line here, this is the isogonic line that will tell me what the magnetic variation is. Somewhere along this line, it will have a degree value. Maybe it's down here. I keep following it. There we go. Look at that. What is the magnetic variation going through my route? 6 degrees east. So I have a 91 degrees true course, and I want to create a magnetic course. What did SkyVector do with that 6 degrees?
Subtracted it from the true.
It did. It subtracted it from the true to get a magnetic course now of 85 degrees magnetic. And that magnetic course is useful to a pilot, not the true course. Okay. So again, targets is not targets. SkyVector is doing all of the math for you in the background. You're just creating your route, and it's already taking into account what the magnetic variation is in that region, and it's giving you your magnetic course. So, but it's kind of nice to know what this means now, right? It's like, yeah, that magenta line really is a true course, but by taking into account the magnetic variation, in this case 6 east, we're able to subtract 6 degrees from 91 to get an 85 degree magnetic course. Any questions on that? Okay. All right, so that's really what I wanted to show you here for the VFR chart, just to kind of see that. I'm going to go to the VOR low. We're going to go look at a few other things. Let me see where I can take us here. Again, just to kind of start us off, I'm looking at the VOR or the IFR low en route chart. This is the chart that is going to be used for aircraft that are flying between 1,200 feet above the ground, AGL, up to, but not including, flight level 180. Okay, 1,200 feet AGL to basically 17,999 feet. And within the low en route chart, this is where you see the the Victor Airways. Okay, these are again the freeways in the skies, but on the low chart, they're referred to as a Victor Airway. And these are the routes and the freeways in the skies that are dependent on the VOR NavAid, the ground-based NavAid. And then if I go to the high chart, same thing. I have routes and freeways in the skies on this chart, but this chart is used for aircraft that are flying at flight level 180 or 18,000 feet up to flight level 450, 45,000 feet. And you can see again that the airways or the freeways in the skies that are being determined and created in black, these jet routes with a J, they are also using the VOR or the VORTAC, okay, to create these different routes. Can anybody tell me what these blue routes are on both the high and low charts? Here's some blue routes over here. This one's a Tango route on the low. What are these blue routes? And how do they differ from these black routes?
They're GPS dependent.
Yeah, the blue ones are GPS routes. And then the black route, again, it's relying on a radio frequency that the aircraft needs to use in order to fly on specific radials out to these different points. So very good. And remember, one more time, for the IFR low chart, you have Victor Airways, which use VORs. And then you have the GPS routes that are listed as a T with a Tango routes. These are GPS routes. And sometimes they overlay on top of another route, and that's fine, that happens. But on the high chart, that's where you're going to find, zoom in here, you're going to find the jet routes. So think jet, they fly higher, right? So you're going to find those on the high chart. The black routes are still radio NavAid dependent, right? They're using the old school ground-based technology. And then the blue routes, or what we call the Q routes, are again the GPS routes. You need GPS to fly and navigate on this routing. Any questions with that? Your VOR routes versus your, say, GPS routes.
Do the T and Q stand for something specific on the GPS routes?
Not that I know of, and I've been doing this for a while. I don't think so. No, not that I know of. Yeah, they're just identified as a Tango route on the low, Q route on the high. And then again, Victor route, Victor Airway on the low, jet route on the high chart. Yep. Okay. Let me go to
is there any
bro.
Is there any meaning to the numbers in the names of these jet routes?
No, it's just a way of being able to identify them. That's just how they're coded. But it's not representing a radial or anything like that. No.
Okay.
No, there's really no meaning behind it. So, all right, let me take you over here. Actually, I'm going to go to a different place here. We're going to cut through some of this stuff. All right. Can somebody tell me what this triangle represents? What is this triangle? And I'll put my mouse there. Sorry, I moved it. What is that triangle?
It's a fix.
That's a fix. Okay. That is a fix. I don't know who answered that. I wasn't able to see it, but if you'd like to answer, great. How would a pilot identify that particular fix on this airway, this freeway in the sky? Any ideas?
With the name?
Okay, we got the name here, right?
Yeah.
So it's always going to give a 5-letter name.
Right.
But that name really isn't going to be helpful to a pilot, right? They're not going to be able to navigate somewhere just based on a name.
But I also have the Airways V12, so you have to go to the Airways and download the Airways, and that's when you find the name and the radial as well.
Okay, and well, let's start with that then. That's a good point. What radial is this fix on off of the Panhandle Vortac down here? What radial is this?
It's off of 045.
045, right? It's on the 045 radial radiating out of this Vortac here. And we know that you guys have told me a Vortac is able to transmit 360 radials, but it's also able to give distance measuring information. So if I'm flying outbound on the 045 radial for 17 DME, I've reached this point here. So we know that the distance from this VOR, this Vortac, to this point is 17 nautical miles. So when we read that distance in our DME in the display, then we know that we've reached that location. So we can give you another example here off of the same VOR. Here's the 081 radial. It creates this Victor 140 route in black. Okay. And then there's a fix out here, again with a triangle and Goonie. Well, we also see, this is kind of a nice airway. It shows me that in a D, inside this D, it says 29 and it's pointing to this fix. What it's done is it's added all of the different segment lengths together to give me the total DME distance from this Vortac out to this fix Goonie. So I can find it as I go 29 DME along this radial away from that navaid. Once it reads 29, I know that I've gotten to this fix named Goonie. Let's look at any questions with that. Does that make sense? Is that going to help? Okay. Let's look at this really quick. Let's say we want to determine the total distance between one navade and the next navade. So this navade here that I'm pointing at and this airway to this navade, if I want to know the total distance, I just need to look for the number that is inside of this box. It's a white box with a black border around it. It says 93. And if I were to add 33 plus 42 plus 18, I'm going to get 93. So that'll tell you your total distance along that airway from navade to navade. Okay. I got a couple other examples here. Let's see. Let's go with this one called broke. Any ideas, you guys? I'm going to zoom in pretty far for a second. Here's the triangle telling me that it's a fix, and the fix name is broke. And then we've got this hockey stick looking thing. I know we got pilots in the group. Somebody tell me what that symbol represents, this hockey stick shape.
Changeover.
Or navigate changeover point. I think somebody else said it. Dan.
Yes, it's called a changeover point. Changeover point. So what's happening is we're going to assume that we're traveling from the Panhandle Vortac again, and we're flying outbound away from that nav aid on the 045 radial until we get to 46 DME. That tells me as a pilot that I've reached this fix broke. At that point, because of this changeover point, I'm going to transition from flying from this VOR, okay, because I'm currently flying away from it, right? Once I get to broke, they're saying, hey, because of the distance, it's a good idea at broke to switch over to the next VOR that you're flying to. In this case, MITB. So at this point, they're going to transition and tune their radios to this VOR, and they're going to now fly on this Vortax 224 radial. Remember, the radials radiate out from the VOR, right? So even though my aircraft is going in an opposite direction than 224, the aircraft is still on the 224 radial. It's just we're flying inbound to the VOR. Okay, so it's ensuring that the aircraft has a strong, reliable signal. And in order to ensure that, they've told the pilots that we need you to switch over from one nav aid source, radio frequency, to the next nav aid frequency. Okay, and that's called a changeover point, telling the pilot to make that transition from one frequency to the next. Any questions on that? Okay. Let's look at the next fix here. That'll take us to the right spots. Oh, I got to type it in correctly though. There we go. All right. Can anybody tell me what this top number is? This 5,400. What altitude is that? Let's go with Brett.
The MEA,
Okay, and what does that stand for?
minimum en route altitude.
Okay, and minimum en route altitude. While I'm on this airway, Brett, if I maintain 5,400 feet, what am I guaranteed as a pilot from the designers?
Obstacle clearance and nav aid signal reception.
Perfect. Everybody get that? If you are at your minimum en route altitude or higher, okay, that will ensure that you are going to stay clear of obstacles as long as you're on this route. And you are also guaranteed to have the necessary radio frequency picked up by your aircraft. Okay, that's your MEA, the minimum en route altitude. What about this bottom number? This 5,000. What altitude is that?
That's a MOCA.
That's your MOCA. Okay, your minimum obstruction clearance altitude. And what does that altitude ensure?
Reception and navigation, I believe.
So it's always obstacle clearance, right? You're always guaranteed obstacle clearance.
Yes.
And you're only guaranteed a reliable navigation signal as long as you are within 22 nautical miles of the nav aid that is creating that route. Okay, so only within 22 nautical miles are you guaranteed a reliable signal at that lower altitude of, say, 5,000 feet. Okay. All right. Okay, so that was the MEA and the MoCA. All right, here's a big giant square. Let's see if I can find a clean one here. Here we go. See the big giant square made up by the longitude and latitude lines? What does this big 5,200 number mean? What is that telling me?
Oroka.
That's your Oroka, right? Your off-route clearance altitude. Okay, that's your Oroka. So it's just saying, hey, if you're not on one of these established airways and you're just flying out here having a good time, we'll guarantee that you'll be clear of obstacles as long as you are at 5,200 feet anywhere inside this big giant square. Okay? That's your Oroka. Any questions on that? And you can see those everywhere. Again, your clearance above obstacles is always different depending on whether you are in mountainous terrain or not. And as a dispatcher, you really don't care, but I just want you to know what these numbers are, right? When you see them on here, you'll at least know that, oh, that's just for those people who aren't on an airway. They know what altitude they need to maintain to stay clear of obstacles. And that's sufficient. Okay. Let's look at another good minimum altitude thing here. Let's do okay. Oh, I took you to the wrong one. Sorry. All right. This is a really important one to understand. I'm looking at this fix, Yokan, with an R in the flag. What does this R tell me?
Minimum reception altitude.
That's your minimum reception altitude. And okay, that's what that R represents. But what does that actually mean? What is this telling me? If you were explaining this to your grandma, how would you do it? Minimum reception altitude. And kind of look at everything that you have pointing to this fix. Any ideas? And I realize that this is all new, but it's good, right? To get your mind thinking a little bit.
It's basically it's the reception altitude to pick up the Tango X-ray Oscar to identify that fix based on that 063 radial off of TXO.
Perfect.
I guess the first thing I do is tell grandma that she doesn't have to pay anything, that there's doesn't have to get any emails or anything like that, and then I would explain.
There you go. All right, so let's assume that my aircraft is at the Panhandle Vortex, and I'm flying on this radial here, the 176 radial, radiating off of the Panhandle Vortex, and I'm trying to identify Yokan, but I don't have DME. If I had DME, that's easy, right? I'm flying away from this VOR on this radial until I get to 29 DME, and I've made it to Yokan. That is easy. This is the radial that I'm flying on, and the nav aid that I'm using to fly on this airway is also equipped with DME, and my aircraft is able to pick up DME signals. Then it's easy to identify this point. But if my aircraft is not equipped with distance measuring equipment, and all I have is a VOR receiver, 2 of them, I can tune into this VOR, fly on this 176 radial, and as long as I maintain a 6,500 foot altitude or greater, I'm going to be able to pick up the signal from this VOR so that I can tune into it and correctly input that radial, that 063 radial in my instrumentation, so that when I'm flying over here, I'm able to determine when I have crossed over the 6.3 radial off of this VOR. And when I see that indication in the cockpit showing me that I've crossed that 063 radial, then I know that I have reached YOCAN, that I'm at that point. But if I'm low, if I'm below 6,500, somebody has gone out there and flight checked this, and they've determined that anything lower than 6,500 either doesn't work at all or it's spotty. You kind of get information and then it drops off. So they're telling you, you got to be at or above 6,500 feet in order to pick up the reception from this more distant nav aid, okay, to identify this point. That's your minimum reception altitude. Okay, any questions on the MRA? Is that making sense, you guys, or is this all just in one ear out the other? You guys good? I need you to be honest with me. Okay. Cool. Good, good, good. And I really am just sharing the pertinent things with you guys. I'm not trying to go into too many irrelevant things. This is really good stuff to know. So just about 10 more minutes here and then we'll go on break.
Hey, Dallin, I had a question.
Yes, Rebecca, go ahead.
It makes sense, but I did want to ask, how would you decide like when to start your climb to 6,500?
You know, that's really up to the pilot. I mean, they could be, they've got to look at all the, excuse me, sorry. They have to look at all the other minimum en route altitudes for these different segments. In this case, I see 5,400 as the minimum altitude. So that's going to be up to them, and it's dependent on the performance of an aircraft. So if they're in a really small plane, right, they're going to need more time to go to a higher altitude than, say, a CRJ 700. So again, it's really dependent on the aircraft performance, and it's really up to the pilot as long as they can be at 6,500 before YOCAN, right? So they can continue monitoring this radial of 063 degrees. But again, that's kind of creeping into the pilot aspect of things. And, you know, not something that you're going to need to be worried about, but very good question. I like the way that you're thinking, Rebecca. And hopefully that was able to answer your question. Let's see, there was another hand. Is that you, Brian? Yeah, that's Brian. Go ahead.
Yeah, yeah. So, and this only, I mean, if you're just cruising along on V81 and you don't care about YOCAN, then you can just ignore that, right? I mean, that YOCAN is used for what, like an approach out of somewhere, or I mean, it has some purpose, but maybe not for everyone.
Mm-hmm.
Okay.
Yeah,
but not necessarily for everybody. Okay.
No. Yeah, not for everybody. There's actually different ways of going to look to see how it's being used. It could be used on maybe just on an airway. It could be used on a departure, on an arrival, on an approach. It could be the initial approach fix for something. There's a lot of different reasons, but You're right. It may not be needed for everybody.
Okay, cool.
And how
I just
would
want
you
to make
know
sure I
that-
wasn't missing something.
Nope, you're good.
How would you know if it's only for an arrival, departure, etc.?
You're gonna know based on if you're coming and flying into a nearby airport, you're going to see YOCAN on, say, an arrival or on an approach. And so if you come across, if you're using something that is using YOCAN, you're going to recognize it as something that's relevant to you. And as a dispatcher, you guys, you're not going to need to. It's really just the understanding of what this flag means. Knowing its use, that fixes use. That's way beyond what you guys need to know. That's definitely more of a pilot aspect that you don't need to worry about. But you do need to know, again, and be familiar with what these different flags and what these different minimums are trying to portray. Yeah. Okay. Just one last thing here, I think. Let's see. I think there's one more. Yep, let's go.
Hey, Dylan, did you mention, I may have missed it, about how to determine VOR or vortex service volume based on the identifier box?
Yeah, let's do that again. We talked about it yesterday. That's a very
And
good,
I guess,
let's do
sorry, my biggest question is that when it doesn't have a notation, what does it default to?
let's see. I don't know if, well, let's look at this. That's a good question. So let's look at this. We've got this VORTAC here. And remember that on the VORTAC tag, on the tag that tells you the name, the frequency, the 3-letter identifier, the lat and long coordinates, and the Morse code. This is Morse code that they can tune into to ensure, if they're using older technology in the aircraft, they'll have to listen to this Morse code to make sure that they're tuned into the right VOR. You'll notice in parentheses here, I've got a VH. So that is telling me that this VORTAC has a new VOR service volume classification as a VH, VOR high. And remember, we said that the VORs that are classified in that way can be used out to 130 nautical miles away because they've been given that strength, right? That's how they've been classified. So VH. If we look at another one over here, Panhandle, this is the VORTAC, and its service volume is an H. So that has the legacy high service volume classification. So it too is also good out to 130 nautical miles. Trying to find another one. Here's one. What kind of nav aid are we looking at here, just by its symbol?
Compulsory point.
Yep, it is a VORTAC that is a compulsory reporting point. And this VORTAC has a VOR service volume of low. The legacy low. Okay, meaning that it's good out to a maximum of 40 nautical miles. Now, Chris, hopefully that summarizes up that portion of it. But your second question was, what if it doesn't have a service volume identification? Is that what you asked?
Yeah, that's what I was asking.
I know this sounds bad, but do you have an example of one that doesn't have it
anymore?
Yeah, I don't know if they don't have it anymore. They're on every single one that I'm looking at. Just know that the ones with the V is going to be the new service volume classification, and the others that don't have the V, like we see over here. Oh man, a lot of these have been updated already. yeah, like over here, this one doesn't have a V, so that's going to use the legacy low service volume classification. So it tells you what the advertised strength is of these VORs. So hopefully that gives you somewhat of an answer, Chris.
And another dumb question, why are there two notations?
So we're not going to get into that completely, but one is for the VOR itself, and the other one is for the DME. The DME also has a service volume, but we don't really share that here. It's kind of, again, goes beyond what you need for dispatch. Same thing over here. First one is for the VOR, the nav aid. The other one's for the DME component. Yep. All right, you guys, any other questions? Those are really good things to talk about. You know, I really hope that you guys enjoyed this portion of it today, just to kind of get into SkyVector, look at the IFR low and high en route charts, and try to make sense of all this nonsense, right, that is on this screen. I get that it's a lot, but at the same time, I want you guys to be able to step away right now and go, you know what? There's a lot on here, kind of complex, because I haven't seen this before, but I get that all these black and blue lines are freeways in the skies. I understand for the most part what these minimum altitudes are now. I know that there are some of these reception flags or crossing flags out there. I know that there's this hockey stick looking thing, a changeover point to tell me when to switch over from one frequency to the next, and leave it at that right now. Okay. As you continue flight planning and as you use this material, that's when you start learning this. That's when you really start to retain the things that we've talked about. But it can get overwhelming. So just try to remember the things that we've talked about today. Come back into the video, into the recording, and watch different aspects of this explanation later on. And you're going to surprise yourself, especially those that don't have any aviation experience at all, the things that you're going to be able to learn and to retain over the next few weeks. Okay. So don't be too hard on yourself. Again, we're here to help you guys out. And we're just trying to introduce you to these concepts little by little, knowing that not everything is going to stick the first time. So, okay. With that, I can stick around for a little bit to answer any questions, but I am going to send you guys off for a 15-minute break, and I'll see you here 45 minutes past the hour. And be excited to come back. We'll talk about the instrument approach plate after our break. All right, is everybody back? I don't know what happened to our timer. It looked like it started and then it stopped, I think. I don't know if it was just because the time was up or what, but I stepped away. So make sure you guys are all here. Trevor, did you by chance notice if that timer was counting down or not? Did it just end?
No, I don't see it up there anymore, but yeah, I didn't know.
Okay.
I didn't see if it was on there.
Yeah. Sorry.
It rang at the 10-minute mark. I think it was set for 10 minutes.
Was it? Okay. That's good. Just want to make sure you guys got your time.
I have a question from just before we went on break. You were hovering over a Nave that looked like a Vortac, but it didn't have any radials coming out from it. Does that mean it was a TACAN?
No, not necessarily. Let me see if I can find one. Hold on a second. Let me bring it back up. I just closed it down too, so I'm sorry. 1 second. And I'll start sharing my screen. I think, let me. There we go. Let's see, we were over here somewhere by the Panhandle Vortac. Trying to think of what you were looking at. You don't by chance remember like the name or anything of it?
Yeah, it was Bravo Golf Delta.
Okay, thank you. Yeah, Bravo. Bravo Golf Delta. Oh, this one. Yeah, it is a Vortac. Looks like, or it's a TACAN, it looks like. So, yeah, it's just not, doesn't look, well, okay. There's nothing radiating out from it. It doesn't have a compass rose. It looks like it's a spot for them to, let's see here, BGD. I actually don't know what they're using that for. It's probably for this airport here. I bet there's no TACAN approach or anything. That very well could be a TACAN that they're going to remove or decommission, and it just hasn't gotten removed from the chart yet. But it had something to do at some point in time with this airport, and there was probably a TACAN approach that used it somehow. But you can tell, see the blue line? That's a GPS airway. And it looks like it's going through, but it's really not. That TACAN has nothing to do with this GPS route. It just happens to be in the same spot as this GPS waypoint easy. So right now, I would say it doesn't really have any function. There's no real use unless it's on the high. Let me see what the high looks like. Yeah. See, it's just sitting out there. I can almost guarantee you that they're probably getting rid of that TACAN, and it just hasn't made it off the chart yet. So good eye. Yeah, I didn't even see that. And I'm going to write that one down to go see tomorrow. What is that thing doing out there? BGD TACAN. Cool. Thanks, Trevor.
Got a little bit of information on it, maybe.
Yeah, I'll get some information on it. Looking at BDG or BGD Airport here, they currently have GPS approaches only to that airfield, which means that it's probably been looked at fairly recently. Yeah, I mean 2018. And they probably just went straight GPS based approaches, and they got rid of everything TACAN or VOR related and got rid of everything and made it a GPS approach only kind of an airport. That's all they have. So, but yeah, I'll see what I can find. And maybe I'll share that with you guys if I find anything on Wednesday when we're together. But yeah, great question. Cool. Anybody else with any questions from what we previously talked about before we dive into instrument approach procedures? Okay. All right, let me get things switched over. All right, so this is another topic that is going to require you guys to give yourself some time to understand and to learn everything that is on an instrument approach plate. We're going to do the very best we can throughout this PowerPoint in the next few days to help familiarize yourself with the instrument approach plate. But keep in mind that the instrument approach plate, again, is used to help pilots navigate down to the airport environment to land in what we call instrument meteorological conditions when they're flying in the clouds. So you're going to see a lot of different altitudes, speeds, courses that they're going to need to maintain in order to ensure that they stay clear of obstacles, keep themselves safe, until they can get low enough and down to an altitude where they can then visually make contact with the runway. And they do that by following the instrument approach plate. And you as a dispatcher, you're going to, again, come to the instrument approach plate to determine down at the bottom what the minimum is, or the minimums, the landing minimums, for a particular airport. And that way you can take that information from the approach plate and make a determination as to whether or not you are legal to go. You'll also use the instrument approach plate to help you derive or calculate your alternate minimums. You'll determine what the ceiling requirement and visibility requirements are for an airport that you have selected as an alternate by coming here down at the bottom of the landing minimum section to make that determination. Again, things that you will do over and over again later on throughout the course. The instrument approach plate is not going anywhere, so you might as well just embrace it and love it and begin to learn the material that is found on the approach plate. And what we're going to do in this class is we're going to take an instrument approach plate and talk about it from top to bottom. And by a raise of hands, how many of you guys were able to watch the video today regarding those altitudes on the airways and the introduction to instrument approach plates? Excellent. I'm telling you guys, that is going to probably help a lot. Okay, I really do think that's going to help. And then for just my understanding, go ahead and lower all those hands. Unless, Brian, do you have a question? Or were you just lowering your hand? Okay. Just so I can kind of get an idea, how many of you guys, let's see, that video, was that anybody's first exposure to instrument approach plates? If so, raise your hand. If that was the first time you really got an understanding or explanation of what an instrument approach plate is. Okay. All right, that helps.
That was first time getting a full explanation for me. In week one and in these, we've been doing these legal to go quizzes. So for those, we do have to go up and look at the, figure out our minimums. So I knew the minimums part.
Perfect. And that's really what, that's what you guys use the approach plate for mostly. So That's good. Okay. Well, again, we're going to try to introduce you to as many things on the approach plate as possible without overwhelming you. But just know that, again, this entire course, the full 8 weeks, is designed to help you in a practical way use the approach plate the way that it's intended for you as a dispatcher, okay? So this class is intended to introduce you to a lot of things more pilot related, so that you become familiar with the approach plate, so that it's not so foreign to you when you're using it in a dispatch related environment. So just kind of keep that in mind. Noah, did you have a question before we continue?
I did not. I didn't realize my hand was still up. My bad.
Oh, you're good. No worries. Awesome. So again, at the end of this particular presentation, this course for the instrument approach plates, you guys will be able to name off the different sections of an approach plate. Okay. And then you'll be able to differentiate between different approach types. We're going to talk about the precision approaches, non-precision approaches, and approaches that are called APV, or approach with vertical guidance. And we're going to talk about the specifics of that. And then you'll be able to name off different segments of an instrument approach procedure. Okay, so we have what's called the final segment, an intermediate segment, and an initial segment. We're going to talk about what all of those are, and what they look like on the bird's eye view, or the plan view of an approach plate here in a little bit. So what is IFR? We've talked about it. IFR stands for Instrument Flight Rules. These are going to be the regulations that are set forth that allow the continuation of a flight into instrument meteorological conditions, abbreviated as IMC. So if somebody says that they're in IMC, that means that they're in instrument meteorological conditions, which means that they are in a situation and in a condition where they are required to use their instruments in order to navigate. Okay? And that the pilots must rely on their cockpit instruments. So there are benefits to flying IFR. And again, we have more pilots in here than I've ever had before. So I want to ask the group, especially my pilot group, what are some of those benefits of flying under Instrument Flight Rules, IFR? Oh, go ahead, Chris. Sorry, it cut off on my end.
Traffic advisories.
Traffic advisories. Perfect. Okay, traffic separation. Love it. Anybody else? Brett, are you a
Going
CFW?
through clouds is a big one.
Okay, clouds. Perfect. You can fly in clouds. Brett, I thought you said your instrument rated, aren't you?
Yes, I am.
Okay, okay. Did you have anything? I couldn't tell who's muted or unmuted, and I didn't want to.
No.
Okay.
You can fly an IF class Alpha airspace.
Oh, good one. Okay, that's a good point. Okay, that is a great benefit. You can fly at a much higher altitude, at or above 18,000 feet when you are on an IFR flight plan. Okay, when you file the flight plan with ATC, you're allowed in that area of the NAS, in the airspace. So that's great. Perfect. And that's where the majority of your flights are going to take place in the airlines. Okay, you're going to be flying at much higher altitudes, and naturally just those altitudes are going to require you to be on an IFR flight plan. And there are a lot of benefits of flying under IFR. And you guys mentioned a lot of those, right? You can fly in instrument meteorological conditions through the clouds. you get air traffic separation. You've got a precise flight path that you've determined, and you've told ATC, this is my idea, this is where I'd like to be, this is where I want to go. And they know that. And everything that you're using to fly under IFR has been designed with the intent of keeping the aircraft clear of obstacles. And that's especially important, right, in these situations where you're flying in the clouds. Your visibility has been limited. You're not able to make reference to the ground. So you rely on all of this material, the IFR en route low charts, your stars, your SIDS, your instrument approach plates in order to navigate from point to point. So I kind of already named off a few of these, right? What are some of the IFR tools used by pilots? Go ahead and name some of them off. What tools do our pilots have to help them navigate while they're in the clouds? Any ideas? Kind of named off a few already, but
You have some additional instrumentation that's required and additional periodic checks of the aircraft to ensure they're all working properly.
Yep, perfect. Yeah, so you're talking about the the equipment on board the aircraft, right? That's a big deal. We've also got things on the ground. What are we looking at here? And we're going to get back to the aircraft instrumentation here in a second, but
Localizer.
We'll forward. What do we got? Yeah, localizer right here. And we've got the glide slope. And what kind of guidance is being sent out with the localizer?
Horizontal guidance.
Yep. Horizontal, lateral guidance, and then we've got the glide slope here providing vertical guidance to the runway. So this is a big deal. This is heavily relied on, again, when trying to make an approach into an airport using these ground-based nav aids. We've also got runway lighting, right? The approach lighting systems. When you're flying in this kind of weather where the ceiling is really low, you want to be able to make out where that runway is as early as you possibly can. And these lights allow us and allow the pilots to see how far away they are from a runway, how they are aligned to a runway. And all these lights mean different things to a pilot. And they can determine distance and alignment. They can increase the intensity of the lighting to meet their needs. So all of this is to help them navigate down safely to the runway. And as mentioned earlier, right, all of the instrumentation in a cockpit is being used to help the pilot realize what direction are they flying? What speed do they maintain? What altitude should they maintain? Okay, all of these different things come into play so that they can navigate safely to the runway environment. And then last but not least, right, everything else that we have been talking about are major tools used by the pilots to navigate in instrument meteorological conditions. We have our IFR low and high chart. I guess I don't have a high chart there, but low and high IFR charts. We have arrival charts helping us funnel aircraft into an airport. And we also have departures. Here's the airport. Departures helping us disperse aircraft out of the airport environment. And also in the center here, we have an instrument approach plate. This one is a GPS approach to a specific runway, runway 34 right, into Salt Lake City. So you can see how the aircraft's going to fly this routing to Salt Lake. Okay. And you can see all the different terrain some water. Okay, it kind of gives you, it paints a picture of the area that you're flying into. This is the Salt Lake Valley. So again, there's altitudes and courses, sometimes even speed, again, that is clarified or depicted on these charts to help the pilots know how low they can go without risking being too close to obstacles. So they're trusting this material here to stay safe. And I know I've mentioned a few times with Chris, he's mentioned you've had opportunities, I think Brett as well, to fly in these IMC, instrument meteorological conditions. And I'm sure that can be nerve-wracking. I've never done it myself. I've experienced it in the cockpit as I've been doing my jump seating. But actually being behind the controls, I've never had that experience. But you really are trusting the values and the numbers that you're seeing on these approach plates to keep you safe. So all of this comes together, and the number one goal is to make sure that pilots are kept safe and away and clear of any obstacles as they are engaging in this type of flight. So any comments from my pilot group? Any experiences with your IFR flying and using this material? It's always fun to hear stories if you got them. Or
Absolutely, yeah. I mean, yeah, I've flown a lot of approaches down to Mins, so it's definitely sporty.
Yeah, I bet.
But it is confidence building as well. I mean, it puts you right there. You pick up the approach lights and you fly it on in. The worst one I ever flew was into Naples. We basically were dodging thunderstorms and we were in holding for 3 hours. And
oh my gosh,
we were out of gas pretty much. So I had to land somewhere. And they said weather good Napoli. Okay, let's go to Naples.
It's good.
It was basically, I think it was everything but lightning hitting the plane.
Oh man.
And like crazy heavy rain, gusting winds. And shot the ILS down to Mins and landed it.
That's crazy.
Also, St. John's, Newfoundland is also a really, really insane sporty place to try to land. Heavy crosswinds, tons of weather systems moving through there. So, but
what kind of aircraft were you flying into, like Naples? Was that the C-130?
Yeah, KC-130.
Oh, the KC-130. Okay. Yeah. All right. Yeah, I couldn't remember. You said it was a 135 or the C-130. So
yeah, the Marine Corps.
The Marine Corps. Okay. Awesome. Yeah, some good stuff. Yeah, Brett, you said you train for you're an instrument instructor, right?
That's correct. Yeah.
So yeah, that's this is good. I love that. I've never had these many pilots or even an IFR rated instructor in here. So this is good stuff. Awesome. Well, you guys, let's talk more about specifics with regards to the instrument approach plate. I mentioned earlier that an instrument approach plate is going to fall under one of three categories. Okay, and that is going to be category number one is the precision approach. It's abbreviated as PA. Then you have non-precision approach, NP, and we have approach with vertical guidance at the bottom there, APV. So a precision approach, PA, is going to be an approach based on a navigation system that provides both vertical and horizontal guidance. This is the important part. That meets an ICAO precision standard. ICAO stands for the International Civil Aviation Organization that kind of oversees the rules of flying throughout the world. Okay. Now, don't worry about these approach types down here, PAR and GLS. For those of you that know what these are, great. For those of you who don't worry about it. I just added this here just to stay true to what this is. But I want you to focus on the ILS under this category, right? The ILS uses, again, those ground-based components of the localizer and the glide slope to provide an approach that gives both vertical and horizontal guidance, and that system meets the ICAO standard in what we call the Annex 10. It's a rule book, if you will. Okay. The ILS and the way it's configured meets their requirements to be considered a precision approach. We're good there? Because when I get over here, you're going to be like pulling hair out. That's why I'm bald. It's because of that APV over there. Not my kids, APV. The non-precision, NP. Non-precision provides lateral guidance only. Again, I realize that right now, a lot of these different approach types do not make sense, and that is okay. But I do want you to kind of think of this as the localizer approach or a VOR approach, right? You guys are familiar with those. The VOR does not provide vertical guidance, nor does the localizer. These two are nav aids that only provide lateral guidance. So if you create an approach using one of these nav aids in this list, it's considered a non-precision approach. Okay. All right. Now let's go over here to the APV approach. These are going to be approaches based on a navigation system that provide both vertical and horizontal guidance, but at a lower ICAO standard than the precision approach. Let me see if I can make sense of that. All of these procedures here provide both vertical and horizontal guidance, but they're using technology that does not meet the ICAO standard to classify it under this category as a precision approach. Okay. LPV is a GPS approach that stands for localizer performance with vertical guidance. Nothing you really need to write down or remember. I'm just trying to give you some info. LNAV VNAV is another GPS approach that stands for lateral navigation, vertical navigation. So these two GPS procedures here both have lateral and vertical guidance, but the LPV approach, instead of using a glide slope antenna that's on the ground, it's using WAAS information, a wide area augmentation system, to help provide a vertical glide path down to the runway. Okay, it's using that satellite-based technology. LNAV VNAV is getting its vertical guidance from either WAAS, the wide area augmentation system, or if the aircraft is equipped with what we call a baro-aided GPS, meaning that it's got a GPS receiver on board and a bunch of other computer equipment on board that's able to take into account the air temperature and pressure in that area to create a glide path down to the runway. So again, as you can see here, just to simplify this, these two GPS approaches provide vertical guidance and lateral guidance, but they're receiving that vertical guidance in a way that is not meeting the ICAO, or the International Civil Aviation Organization's standard. So they've said, sorry, we've got to categorize you as something else. We can't categorize you as a true per definition, precision approach. Okay. All right. So again, precision, non-precision, and then APV. And I will say that this concept is important to know, especially the precision and non-precision thing. It's a bonus if you can understand this. Don't overcomplicate it. Just know that it's categorized as something different because of the way that it's getting its vertical guidance. It doesn't meet the standard. Okay. Now your precision approaches, it's like which of all of these precision or approach types will provide the lowest minimums? Well, it's going to be the precision approach. Okay, that's really where we want you to focus your time and attention, right? Like, why does the dispatcher care about this? It's because when you have 50 some odd flights on your desk that you're trying to dispatch, and you're trying to find an approach that provides you with the lowest possible minimums because weather may be really bad that day, I don't want you spending time looking at VOR and localizer approaches, right? Because you'll never have lower minimums on a non-precision approach than you will on a precision. So again, we're trying to help you see that if you're looking for the lowest minimums possible, you better start looking in the precision approach category. Start looking for the ILS, because that one is the least restrictive, right? It has the greatest the lowest minimums on the approach. Okay, so you're going to find the lowest minimums on an ILS approach. You're not going to find the lowest minimums on a localizer or VOR approach. Now, bonus points for somebody who can tell me and remember, what are the lowest landing minimums for a standard ILS approach?
I think it's 200 feet and a half statute mile visibility.
Perfect. Excellent. Okay. So as you can find, if you can find that ILS and it has those kind of minimums, then you can continue on making other decisions a lot faster as a dispatcher. And that truly is why you care, why you should be able to look at an approach and go, oh, that's a VOR approach. That's considered a non-precision. Or, hey, I'm looking at an ILS. This is a precision approach. It provides both vertical and horizontal guidance, and it meets the ICAO standard. Okay, so that's really why we care. We've got a few more minutes before we go on another break, and I'd like to just introduce to you guys and give you kind of a field trip, if you will. This section is not one that you really need to take notes on. It's more just informational. We've added this in here a while ago, and it's kind of fun to see and understand, how are landing minimums determined? How do all of these values, all of these numbers and altitudes get determined and then ultimately displayed on an instrument approach plate? What goes on in the background? How is this happening? And that's really what we want to share with you guys today. But again, I always want to emphasize, this is just like going on a field trip. It's informational. Nothing here will be tested in your week 5 test. So don't worry about that. Okay. So it all starts here with different procedure designers, different specialists that work over at the FAA. They use what is called the FAA Order 8260.3. It's a big document that helps you determine the different methods for designing and evaluating instrument approach procedures here in the United States and in its territories. And within this order, this FAA mandated order here, the 0.3, there are a lot of different sections in there that tell us about creating an intersection fix and the different angles and the different positioning of the VORs, the vortex out there, and how they can be positioned. It helps us determine how to create departures out of an airport, how to determine the different minimum visibilities that you see at the bottom of your approach plate. Okay, there's a table that is referred to, and it tells us, okay, with this different minima, I can have this visibility requirement. It also helps us determine different minimum altitudes over obstacles. Okay, so there's a whole manual that instructs and tells you the rules behind creating different aspects of an approach and what can and can't be done. The instrument approach is comprised of a few different segments. You have what's called the feeder route, which helps bring in aircraft from the freeways and the skies, right, onto the approach. It leads to an IAF, which is an initial approach fix. So you got your feeder route feeding you in. It's kind of like the off-ramp from an interstate, right? And it connects to the initial approach fix, where you begin your descent down to an intermediate fix, IF, and then ultimately down to what we call the final approach fix. And at the final approach fix, you guys, you are about 5 nautical miles away from the airport. This is where you will typically hear the landing gear drop on the aircraft. If you've ever heard that, right? Where it drops, that's about 5 nautical miles out or so. And that typically is happening over this area, over the FAF. And then as you descend down, we also create a climb to climb back out if needed, which is called the missed approach. And the missed approach will get you to a safe altitude to begin a hold so that you can make the determination of whether you want to go back and try the approach again, or if things aren't working out at that airport, you can go to an alternate airport and you would communicate that with ATC. Okay, so again, the different segments of an approach are the feeder, the initial, intermediate, and the final approach fix. And we can't forget the missed approach, right? That's always part of it. If you got a way in, you got to have a way out, just in case. Now, each of these different segments of the approach have an area around it, and you can see those areas in red, kind of like a boundary line. And each of these different segments evaluate for obstacles in each of these different segments. Okay, all the way through the missed approach and even the holding. See this, the pattern here? This is a holding. Everything is evaluated for a controlling obstacle that ultimately determines your minimum altitude. So once you find the obstacle in that segment, there's typically a line that is drawn on top of that obstacle. And the specialist, once they determine that obstacle, they'll say, okay, I know the controlling obstacle, but I want to keep my aircraft far away from that tower. So they provide a buffer. It's called a required obstacle clearance, a ROC. It's a buffer that says, okay, we found the controlling obstacle. Now I want my pilot to be way up here rather than being right at the obstacle's height. So you provide a buffer. And with that buffer, that becomes your minimum altitude. So when you see minimum altitudes on an approach plate, that's how that minimum altitude was determined. They found the obstacle, provided a buffer, and whatever altitude you have after adding that buffer becomes that minimum altitude to keep them clear of these obstacles. And all of that information, you guys, is compiled and gathered into these forms. And you can even see here within this form, look at this area. You guys are familiar with this area. This is your landing minimum section. It'll tell you your minimum DA, your decision altitude, or your minimum descent altitude, along with the visibility for each of the aircraft categories. So that gets compiled into these forms. And once everything, all these altitudes and courses and distances get added to this form, that gets sent over to a charting department, and they're able to create from what has been added on the form, and they put it into a nice graphical image for the pilots to use with, again, their minimums, their routes, their headings, the courses, the speeds, everything is added here. And once the approach plate has been created, it gets sent over to a group of pilots that will take that information and they will go fly that approach in good weather, in VMC or visual meteorological conditions, with a mission specialist in the background, making sure that those VORs that have been used at those different altitudes are working as they should, right? We talked about those minimum reception altitudes. Well, somebody's back here going, ooh, if they're any lower than 6,500 feet, they're not going to be able to pick up that crossing radial. That all happens here with these pilots and this mission specialist. And they will go back to the specialist who designed the procedure and say, hey, that 4,500 foot altitude you put out there is not high enough to pick up the signal from this VOR. Let's go ahead and raise it to 6,500. Okay, so there's a lot of communication going on with regards to the development and the maintaining of an instrument approach. And this is one of the king errors used by the FAA. You can see check underneath the wing. This is just one aircraft type that they use to fly different procedures that are being either developed for the very first time or procedures that are being amended and modified and updated to current criteria standards. So, and then in the end, once it receives a satisfactory flight check, they get published on a specific date for the rest of the public to use. So, yeah, that's basically how an instrument approach plate is born. It goes through that process, follows rules. You put a fence around an area, a flight path. You look for obstacles in that area, determine these minimum altitudes, document it. It gets charted as an approach plate, and then somebody flies it to make sure that it's A, safe, and B, logical, right? You don't want something overly complex that is too demanding on the pilots. So all of those different aspects are being looked at during the development phase. So with that, you guys, let's go on an early break. We're just a few minutes from the bottom of the hour. Let's go ahead and let's be back at 40 minutes past the hour, please. Okay, and we'll see you then.
Hey, Dallin, you still on?
Yep, I'm still here.
Is that a King Air 350 they're using for that?
The exact type, I'm not sure. I think it's a 5-bladed prop.
Looks like it.
or a 4-bladed prop. I'm not sure which variant that is. November
That-
7th, I think that's here in Oklahoma, actually.
Yeah, it's one of my favorite planes.
Is it? Yeah.
Yeah, the thing was fantastic to fly.
Yeah,
That
one of
tour.
my managers flew that one. No, not my manager. I'm sorry. One of the guys that I worked with, he actually flew on this exact King Air as a flight check pilot.
Okay.
So
Yeah, I was flying out of Miramar down in San Diego.
okay, yeah.
I was the lead instructor on that for the Marine Corps base there.
All right.
And so it's mostly, we do VIP, we do a little bit of cargo, but mostly VIP flights.
Yep.
Most of our flying was just training, and we literally would just go out into SoCal, which was for like 4 hours until we ran out of gas. It was like the most amazing flying.
Oh man, I bet. Yeah, that is so cool. That is awesome. Yeah, it looks like online, you may know better than me, but it looks like it's a Beech 300.
Okay, yeah, it might be.
Or,
Tell exactly. They look pretty similar. They got the winglets and
yeah.
everything. So
Yeah, looks like that N number there. Yeah, it's okay. This is actually from an FAA source. Model 300. Yep.
okay.
Wow, manufactured
It's the same.
year. That one 1988.
Holy crap.
Yeah,
they,
I didn't
they
realize all
upgraded,
that.
they completely upgraded it.
Wow.
Dual FMS and
Oh yeah. Oh, now okay, hold on. Sorry. This
the
image
inside,
is not that aircraft.
not that
I-
plane. Yeah, I was gonna say
No.
that. There's no way.
And honestly, I think this image is actually from this is a public
Is that the-
company.
Okay,
That-
'cause they fly Gulfstreams a lot to do like the ILS testing. I don't
Yep.
know if that's what this one is. Okay.
Yeah, they do. They do that as well. So I think this is still a King Air aircraft. Look at those windows.
It does look like it, but I mean, it's Gucci'd up, but it still
is.
does
This
look
one-
like a King Air.
Pretty dang fancy. Look at that.
All right, my friend, I'm gonna go take a break.
Yeah. All right. Looks like we've got what, another 50 minutes or so. So hopefully you guys can stick in there with me and we'll get through this material and we'll call it a night. So any questions up to this point? Everybody feeling okay? Not too worried about my pilot group. I'm more obviously concerned about my my no aviation experience folks, right? This is, I get it. It can be overwhelming at times, but let's I'm trying my hardest to make sure that that's not the case. So again, let me just keep throwing things at you and hopefully your Velcro suit sticks, right? Something sticks to that. So, okay. All right. So these instrument approach plates that we've been looking at, or just kind of showing you, they are divided into different sections. And in order to make sense of all the information on the instrument approach plate, you really have to look at the instrument approach plate from a different perspective. You really have to step back a little bit and look at it in a way that breaks it down into smaller pieces. Because if you look at the instrument approach plate as a whole, it can be very overwhelming and information overload. The Jeppesen legend, remember how I told you there's a legend out there from the from Jeppesen and the FAA. Those legends have a breakdown of a blank instrument approach plate to kind of help you understand the different sections of the approach plate. And those different sections consist of a heading, communications, the approach briefing information, something called the MSA, which you will need to know. It's called the minimum safe altitude. We'll break that down here in a little bit. You have what's called the approach plan view. This is going to give you that bird's eye view of the entire approach. Then you have the approach profile view, which gives you a depiction of the approach from the side. Different conversion tables, different icons that we'll talk about here in a minute. These icons help a pilot visualize what the missed approach instructions are, what altitude they need to climb to, which direction they're going to turn, and ultimately where are they going to be holding during that missed approach. And it's all done not with words, but down here it's done with different icons. And then for the dispatcher, your most important part is the landing minimums section. Okay, down here at the bottom. So again, these are the different sections of an instrument approach plate. And what we're going to do now is take some time to break down an instrument approach procedure, an instrument approach plate from top to bottom and kind of show you these different sections. Okay, again, this is meant to be the introduction. Okay, just me taking the time to introduce you to an instrument approach plate and point out some of the items that are found on the approach plate. And because you guys have seen the video, I'm hoping that this is more of a review of what you've seen. And if you need to, go ahead and ask questions for more clarification, okay? So here we go. In the center of the screen, I've got the filled in instrument approach plate. And in the top right, you're looking at, again, what I had here, but that information is blank. So I'm just trying to point out which area of the approach plate you're looking at. Okay, and we're looking at the top portion of the approach. Within the top portion of the approach in the heading, it'll give you the airport code, okay, KEUG, and then the name of the airport. It'll give you some dates to tell you when did this approach come into effect, how long is it good till, okay, things that you'll learn as you begin using this. It's not too crucial right now, but those are the dates at the top. You also have the city and state of where this approach is located. And in the top right, we also see what kind of approach this is. This is an ILS or a localizer to runway 16 left. So you can either use both the localizer and the glide slope to fly this as an ILS approach, or you can choose to fly this as a non-precision approach and just fly the localizer part of it. Okay, and it's all aligned to a specific runway, runway 16 left. So that means that there are some parallel runways going in the same direction, and they have to be able to differentiate between them. Okay, left, sometimes they're center, and right. So you'll see L, C, or R. For the communication portion, that's this line right here. This is going to list out different frequencies that are needed while you're progressing through the approach. And all of these different frequencies are laid out in the order that you are going to need them. So ATIS, does anybody know what ATIS stands for? ATIS. Okay. That's going to be your automatic terminal information system. This is where you would tune into this frequency and get information regarding the weather and the current configuration of the airport. Are they landing to the south or are they landing to the north? What's currently happening at the airport right now? Okay, you're going to get that information. And then you have information about contacting approach, possibly needing to contact Seattle Center whenever the approach controllers is in op. They give you like an alternative way of reaching somebody. And then you would contact Tower, the Eugene Tower, on one of these frequencies, depending on which runway you are landing on. And then once they give you clearance to land the tower and you're on the ground, then you would need to contact ground on this frequency to receive instructions from those controllers on how to navigate from the runway, the taxiway that you just exited from, and get to, say, the gate or the ramp. Okay, but those are the communication frequencies. Then you have the approach information right here. You have a frequency here for something called the localizer that you guys are familiar with, right? This is the localizer identification. It has a 4-letter code, and all localizers, their codes all begin with an I, followed by three more letters. In this case, this localizer providing the guidance to the runway is IADE, and it's on this frequency of 111.75. Now, when the pilots tune into this frequency of 111.75, they not only receive the localizer lateral guidance information in the cockpit, they will also pick up the glide slope information. Okay, it's all tied to this frequency. Over here on the right-hand side, we see what the final approach course is going to be. So the pilots know that once they are established on the final approach course, they will be on a 163-degree course. The GS here stands for glide slope. And this is telling the pilots that they are going to begin receiving that vertical guidance information over this specific fix, Zunax, at this altitude of 2,000 feet. MSL, mean sea level. Okay. The altimeter inside the aircraft that they're using, they're looking at it from an MSL perspective. Mean sea level. So when the pilots are on this final course of 163 degrees, they're established on the final, and they're at 2,000 feet and they get to Zunax, the pilots can expect that the glide slope information is going to come in, and they're going to begin following that glide slope information so that they can maintain a nice constant rate of descent down to the runway. We also see here that this area will call out to the pilots what the minimum is as far as the decision altitude, and we'll go more into this later. But there's an altitude that the pilots need to know when they are flying on an ILS approach. They need to keep this minimum in mind, 569. So while they're on that glide slope, they're going to descend all the way down until they get to 569. They're going to make a determination at that altitude to say, can I see the runway environment? Can I continue down below this altitude? Or do I need to begin or execute my missed approach, where they need to begin climbing out again to a safe altitude because they can't make out the ground or the runway environment at that decision altitude. Okay, this is with an ILS, an instrument landing system, or a precision approach. Okay, and then here you got more information about the airport elevation, 374 feet. And then does anybody know what this TDZE stands for? Anybody else? Brett, oh, go ahead. I didn't know your hand was raised. Sorry.
Yeah, no problem. It's a touchdown zone elevation.
Okay, your touchdown zone elevation. And what that is your highest point within the first 3,000 feet of the runway. Okay. Now, I told you that the minimums here was 569 feet. Okay. That's your decision altitude. So if I'm at my decision altitude of 569 feet, I am going to be at an area where my, well, let me just do it this way. If we subtract 569 from our touchdown zone elevation of 369, that leaves me with 200 feet. Okay, so what that means is that at my decision altitude, I get to 569 as I'm descending. That tells me that I am 200 feet above the runway at that location. And I'm going to kind of draw that out for you here in a little bit. But that's essentially what it's saying. So these are important numbers to know. So you have an airport elevation, which is the elevation of the geographical surveyed center point of the airport, 374. But the area that I'm landing on, the highest point within the first 3,000 feet of that runway is 369. And that's important to the pilot because that's the area that they're going to be landing on. Okay, so those are the values that are depicted and documented there for them to see. All right, down here you have the missed approach instructions. So there's a lot going on in here, but if we break it down a little bit, you guys are going to probably be surprised with how much you actually know what's going on. So if they get to this decision altitude of 569 and they look up and they can't see or make reference to the runway or the airport, they're going to have to execute a missed approach and they're going to follow these instructions. It says that they need to then climb to 5,500 feet on this heading of 163 degrees, which look, that's just a continuation of what they've been doing this whole time. So they're just going to continue climbing up to 5,500 feet on that same 163 heading. And they're going to outbound. They're going to fly outbound on the 152 radial. So if you think of a VOR, think of the radial 152, and you're going to do all this right now in your head before I advance the slide to show you the image. But you've got a VOR with a radial 152. They're going to get onto that radial and fly away from the VOR to a point called Sagen. And they're going to know that they are at Sagen when their DME reads 16.0 while they're flying on that radial. And when they get there, they're just going to sit there and hold until they make a decision as to what they need to do. Okay, so let me go back over here, advance the slide, and kind of give you an image of what's going on. So they're flying on this bold black line. They get over here and they can't see the runway. They're going to climb, and look at the dashed line now. This is the missed approach. They're then going to climb to whatever it said, 5,000 feet, I think. Yeah, 5,500 feet. And look at this VOR here, EUG. It's got that radial 152. They're going to fly until they intercept that radial, and then they're going to fly on that radial. If we come over here, it kind of shows you a continuation of that. It's just not to scale. But they're going to fly on that 152 radial until their DME says 16.0. And once it says 16.0, they've reached Sagen. And they'll hold over Sagen until they can make, further communication with ATC and make a determination as to what they want to do. Okay, but that's the missed approach instructions. And then down here you have additional information for the pilots to see. Nothing too pertinent to the dispatcher other than this procedure here tells me that there are some notes where the DME, or the distance measuring equipment, is required on board the aircraft. Okay. And then over here we said the MSA was something we needed to know about. That's your minimum safe altitude. That's this section right here. And this minimum safe altitude communicates to the pilot the altitudes that they need to maintain if they find themselves in an emergency situation where they need to know immediately nothing other than, hey, how high do I need to be in order to avoid obstacles? Okay, there's a center point here. In this case, it happens to be the Eugene VOR is the center point. And they know that they can kind of figure out what sector they belong in, or where they currently are, to make the determination that, okay, I'm over here in relation to the VOR, I need to maintain 5,300 feet, or they may be in this piece of the pie, and they know that they can be safe a little bit lower at 4,600 feet MSL. Okay, we're talking about engine failure kind of stuff here. Okay, where they're not able to make a communication or get in touch with ATC. And it could be a number of different reasons, but this MSA really is intended for emergency situations, to let the pilot know that, hey, if you know where you are in relation to this center point, as long as it's within 25 nautical miles, if you can maintain these altitudes, you are guaranteed obstacle clearance. Okay, so again, emergency situations, the minimum safe altitude. Okay, so that takes care of that top portion. Then you have the bird's eye view of the entire approach. I'm not going to go too crazy with all this stuff, but again, this big bold black line is your course that is being flown. You have different points along that course. You see different DME distances here. For example, Zunax. Zunax, you know that you're at Zunax when you are 6.1 DME from what? The localizer. See how it says IADE? It's saying that the localizer over here has DME paired with it, and it's able to display or provide distance information to the pilot. So as they're flying on this course and they see 6.1, they know that they have reached Zunex. Again, terrain information, but it's really just a bird's eye view of the entire approach. All right, so down here you have your landing minimum section. We kind of went down to the bottom for a second because I really want to emphasize before I begin talking about the profile view, that side view of the approach. I want to first make sure that everybody understands this important concept. If you have an approach that has vertical guidance with it, I don't care if it's a precision approach or that APV approach that we talked about. If you have vertical guidance, okay, you're being guided down vertically, that kind of approach will always have what's called a DA altitude or a decision altitude. Okay, got to keep that in mind. Now, anything that doesn't have vertical guidance, meaning it's a non-precision approach, lateral guidance only, it will have an MDA, a minimum descent altitude. So again, decision altitude for vertically guided procedures, minimum descent altitude for those that are guided down only laterally. Okay, leaving the vertical guidance up to the pilot in their calculations. Okay. Now we can go back, or any questions with that regarding a decision altitude versus a minimum descent altitude? Because that'll be important to understand for this next section. All right. So again, now we're just moving back up to the approach plate. Now we're back where we need to be. So we were at the approach plan view. If we work our way down, the next one is the approach profile view. So we went from a bird's eye perspective to now the side view, the profile view of our approach. Here is the runway, this bold black line. Okay. You have your different fixes here with their names, FITMA, Zunex, Holta, okay? And you also have this feather looking thing. That's just showing you the glide slope frequency that's being sent out to the pilots, okay, to the aircraft. Okay, and then you also have these different lines. You have more of a solid black line, and then you have a black dashed line. The more solid line right here is representing the ILS or the precision approach. The dashed line here is showing more of the non-precision approach. Okay, it's not being guided down vertically along a nice slope. It's really just telling the pilots what the minimum altitudes are, and they have to come up with the calculations to determine how to descend. Okay. Now, what I'd like to do is I'd like to take you guys through two different scenarios. The first scenario will be what happens when a pilot decides to fly this approach as a precision approach, meaning they're using the glide slope to fly down to that decision altitude. And the second scenario will be the non-precision scenario where the pilot knows that they can't descend down any lower than their minimum descent altitude. So I like to call this section our chair flying section. We're going to fly this approach together and talk through what is happening and the decisions that need to be made by the flight crew. okay, to help understand these concepts. So I'm going to try to use my pen here, but it doesn't always work, so I apologize. All right, so the first scenario is the precision approach. Can somebody remind me what type of altitude, what type of minimum altitude is associated with a precision approach, one that has vertical guidance? What did I say? Anybody? Crickets.
The decision altitude?
Yes, a decision altitude, a DA. Okay, now if I go back a slide, or I'll just go, I'll go back a slide. The decision altitude for this precision approach is 569, okay? That's the number to remember, 569. I'll put that here. Oh, see, it's doing funky stuff. 569. It has a birthday hat for anybody who has a birthday today. Okay, 569. So we are going to chair fly this, and we're going to say that my aircraft is right here at 2,000 feet, and we're going to continue flying until we get to Zunax. Okay, Zunax is where my aircraft is going to intercept the glide slope. And what kind of guidance do we get from the glide slope? I know it's really redundant. We keep talking about it, but
vertical guidance.
Vertical guidance, right? You get vertical guidance here. So if I'm at 2,000 feet, I'm flying until I get to Zunax, and somebody remind me, how will my pilot know that they've gotten to Zunax? Any idea? I'm trying to zoom in here a little bit for you. I'm at 2,000 feet flying. How will I know that I'm at Zunax?
6.1 DME.
Yep, 6.1 DME from the localizer. So they're going to look at that information in the cockpit, and they're going to watch that count down, right? From 10, 9, 8, 7, and then eventually 6.1. And they're going to start seeing the glide slope information coming in. Okay. And once they see that, they're going to follow that glide slope all the way down on this solid black line. That's what it's representing. And they're going to fly the glide slope until they get to their decision altitude. What was our decision altitude? 569. Okay. And at 569 right here, they're going to make that determination, a decision to either continue to land or they'll have to go missed. And they'll continue to land if they can make reference with either the runway itself or some of the lighting. They can descend down below that 569. If they can't make reference to anything on the ground with regards to the runway or the lighting, they are forced at that time to go missed. They have to immediately start climbing to 5,500 feet and following these instructions here to their holding point, Sagen. Okay, that we talked about earlier. Again, this is the process for flying a precision approach, one that is vertically guided. You follow the glide slope all the way down to a decision altitude. And then at that time, you have to make the decision to either continue or to go missed. Any questions with that concept before we move on to the non-precision scenario? And again, I apologize for all the crazy markings. They using that pen on here is difficult. Kind of goes crazy. So I'll put the decision altitude back here, so we have it for later. That was 569. Now let's look at the scenario for the non-precision approach. So what did we say about the non-precision approach? What kind of altitude is associated with that?
Minimum descent altitude.
Minimum descent altitude. Perfect. Sorry, I'm just letting somebody back into class. Yes, your minimum descent altitude. And if we go back a slide, our minimum descent altitude, say for the localizer, is 700 feet. So let's go back. 700 feet now, okay? You guys can look at that value there. All right. Perfect. So again, we have our aircraft at 2,000 feet. And I want to point out a symbol here that is only pertinent to the non-precision approaches, those that don't have vertical guidance. It's this little symbol right here. Any ideas what we call that? There's a specific name for it that we throw
Maltese
around.
cross.
Yes, that's the Maltese cross, okay? Okay, so the Maltese cross, perfect. So we're going to fly at 2,000 feet. We're going to get to our final approach fix, which happens to be at the same location where our precision approach intercepts the glide slope. Okay, it's at this Maltese cross, okay, 2,000 feet. At this point, when the pilot knows that they've reached Zunax, they now know that they can descend down to a lower altitude. Okay, in this case, from Zunax to Hulta, and again, Hulta is called a step down fix. It's just telling me that, hey, between these 2 points, I'm going to tell you what your minimum altitude is. This is as low as you can possibly go between these 2 points. So between these 2 points, my pilot knows that they can descend down to nothing lower than 820 feet. And the reason for that is because there's some sort of obstacle here. Okay, there's something here that is restricting them from going down to their minimum descent altitude of 700. They can't go down to 700 yet between these 2 points. So they stay at 820. Okay, and then once they get to Hulta, then they say, okay, we got to Hulta because I'm looking at my DME 2.4. And I now know that because I'm at Hulta, I have safely overflown this obstacle back here. So now they are able to descend down to their MDA, their minimum descent altitude of 700 feet. Oh, I don't know what it's doing. Sorry, guys. 700 feet. Okay, now they can descend down lower. And with a minimum descent altitude, you don't have to make any decisions yet, right? This is just telling you how low you can go. It's your minimum descent altitude. You can fly that minimum descent altitude all the way out until you get to a point called the missed approach point. Okay, this is telling me that this is as far as you can fly at that altitude before you are forced to execute a missed approach if you can't see the runway environment. Okay, so now let's walk through this again. Just this MDA portion, right? So we're at 2,000 feet. I get to Zunax. I know that it's safe to descend down to 820 feet. Okay, 820 feet. And I'm going to continue flying until I get to Hulta. And then once I get to Hulta, I know that it's now safe for me to go down to 700 feet. And ideally, I'd like to continue flying until I get to a point like right here, and if I can see the runway environment, well, then I'll continue to descend and land. But if I can't, they can continue flying forward again until they see the runway environment, but they can't pass the missed approach point. Okay. And the longer the pilot waits and the closer they get to the missed approach point, they're essentially creating a much steeper descent profile. So they want to see the runway like way back here if at all possible. Because if they wait all the way to the missed approach point, look where the missed approach point is. It's right at the runway. So if they get right at the edge of the runway, depending on the aircraft type and the length of the runway, they may not be able to maintain what we call a stable approach. And they may just continue, and they should, execute a missed approach at that point. Okay. But again, that's a minimum descent altitude where they're given these different minimum descent altitudes to stay at or above until they get to a point where they've gotten to their minimum descent altitude and they can see the runway environment, then they can continue down. So that's the difference between your decision altitude, where you absolutely have to make a decision. Let's see if I can delete all this. Oh, of course, it's not going to delete that. Just going to keep it there. I don't know what's going on. So yeah, you make a decision at this point. If you can see the runway environment on a decision altitude, precision approach, then you'll continue. If not, you'll have to execute a missed approach. And on an MDA, you descend down to these minimum descent altitudes. And again, it's associated with a missed approach point, meaning you can fly that minimum descent altitude all the way out to this point. That's the farthest point you can travel to at that altitude before having to start your missed approach. Okay. Any questions with regards to the difference between a decision altitude and a minimum descent altitude? Does that all make sense, you guys? Okay. It's all in the name. It's all in the naming of that decision altitude versus minimum descent altitude. If you can remember those acronyms, that'll kind of help you remember that, those precision approaches have an altitude where they have to make a decision right at that altitude. And the other one, the non-precision, they have a minimum descent altitude. They have time. Once they get to that altitude, they can be there until they see the runway, but they can't pass a certain point. Okay, and that point is the missed approach point. Okay. Oh man, is that going to stay on everything? That's ridiculous. Here, let me stop sharing, and I've never seen that before. There we go. May have something to do with me just sharing my screen. I don't know. It went away. All right, so now we're getting to the very bottom of our instrument approach plate. Okay, the landing minimum section. On a lot of these Jeppesen charts, you may see in the top left-hand corner a term that says TERPS. And no, this has nothing to do with marijuana. This is the Terminal Instrument Approach Procedures icon that just lets people know that it was using the rules that we talked about earlier. Remember that FAA order, the rule book? It's just saying that it's using those rules to create this procedure and ultimately determine what these minimums are, both your ceiling and your visibility minimums. So again, with this landing minimum section, this is really the most important section for you as a dispatcher. right? This will tell you that these are the landing minimums for the runway 16 left on this approach. And these are the minimums for the ILS, so the Precision Instrument Landing System approach. Your decision altitude is 569 feet. And if you look here on the left-hand side, you have the different aircraft approach categories. And in this example, every category is given the same visibility, but that's not always the case. So please be careful. Sometimes you'll see different visibility requirements for different aircraft types. So remind me, what is the aircraft category for the CRJ 700 that you guys are dealing with in class?
Category C.
Yes, it's a category C. So please make sure that you guys are looking at the right aircraft category column as you're looking at these different visibilities. There will be a time where an employer, or even here in class, an instructor is going to try to trick you when they ask you, based on these minimums here for the CRJ 700, what are the minimums for the ILS? And if you see that the visibility values are divided up and different for different aircraft categories, you need to make sure that you're looking at the right aircraft category for that aircraft that you are dealing with. In this case, they're all the same, so it doesn't matter. So you'll also notice two different columns under the ILS and under this localizer. And this is telling us that your visibility values will be different depending on whether or not you have the approach lighting system working. Remember, those are those lights around the runway, right? If those lights are working, you're going to get a much lower visibility minimum because you're going to have the assistance of the lighting to help enhance the visibility for the pilots, right? You have that help. But if those lights are out of service, the approach lighting system is out, look what happens to your minimums. They go from a half statute mile, now they've increased, telling you that you're going to need better visibility to shoot this approach or to fly this approach because you don't have the help that you once had from the lights. Okay. Now, over here on this side, this is telling me that this is the localizer. This is the approach using just the localizer navigation. So you're only getting lateral navigation. Naturally, your minimums are going to be higher. Okay, you're not being guided down vertically. So because of that, they have to increase your minimums to ensure that you stay clear of obstacles. So 700.5 when your lights are working. But if your lights are out for the localizer, they now go from a half all the way to 1 statute mile. And then you have circle to land minimums. We're not going to talk too much about circling to land minimums, but what this does is it allows the pilot to fly towards runway 16 left, and then last minute, they'll kind of break away from 16 left, and they can circle to land at another runway, as long as they've made visual contact with the airport environment. Okay, now in the airlines, even at SkyWest, as a dispatcher, I had to remember that the lowest landing minimums that I could ever have for circling was 1,003. So 1,000-foot ceiling and a 3-mile visibility, unless the minimums showed higher on the approach. And in this case, you can see nothing is over 1,003 other than this Cat D here, but that's not something that a lot of airlines will do. Some of them don't even authorize their pilots to fly circling to land minimums, from what I've heard. So they just don't train on it. But anyways, that's what this is over here, your circle to land, where they can break away and circle to another runway. Again, this is where you guys have spent the majority of your time, right? Over here in the landing minimum section, determining what is my visibility minimum so that I can make that determination on whether or not I am legal to go. What is my ETA to my destination? I need to look at the forecast, and I need to determine, okay, I know based on the NOTAMs and this approach that I have a half-mile visibility requirement. That's my minimum. Now I'm going to go to the TAF, the forecast, at say 1800 Zulu, because that's my ETA, and do I see a half statute mile or better of visibility at 1800? If I do, then I'm legal to go. If not, I'm not legal to go, and we're going to have to delay the flight. Okay, that is the reason why this is so important. You need to be able to come here to an instrument approach plate, go down to the landing minimums, and determine what your minimums are. And you also have to take into account any NOTAMs, right? That could say, hey, your approach lighting system is out. Well, now knowing that the approach lighting system is out for runway 16 left, I know that I have to look at this column now and increase that minimum and not a half. And they will get you. Okay, either here in class or in an interview, you will see a NOTAM and they're just going to wait for you to fall on your face and say that your minimums are a half when really it should be 3/4. Okay. All right. Well, to end, you guys, I just wanted to recap really quick, not a test, right? But we've got the feeder segment, the initial approach fix segment, the intermediate, the final, and the missed approach. These are just different terms that I want you to hear. You may forget them, and that's okay. You're not going to be tested on it in this class. I just want to show you that these are the different segments of an approach. And again, we've talked about how obstacles are determined in each of these different segments to help create and determine what the minimum altitudes and visibilities are going to be along the approach. Okay. And then just a reminder, just because we're short on time, non-precision approaches have lateral guidance only. That's these. These here in box A are approaches with vertical guidance, APV, and then the ILS is considered a precision approach. Okay. Now, let me just get through all of this stuff. Some helpful resources here. Again, within this PowerPoint, I have included a link that you guys can go to access the Jeppesen legend. So it'll go over instrument approach plates, the IFR low and high en route charts. Okay, all the different symbols that we talked about today are in this PDF document to help you understand different symbols in these different areas, including the en route stuff that we talked about today, the low and high en route charts, and also our instrument approach plates. I've also included for later on down the road, when you're just dying to open up a large textbook, you guys can go and use, this is a free resource from the FAA called the Instrument Procedures Handbook that will go and break down everything about an instrument approach or the low and high en route charts, also the stars and the SIDS. So if you ever want to learn more about those in much greater detail, you guys have a resource here from the FAA to access. And this is a great read. I mean, there's a lot of material, but as you begin exposing yourself to this material, these will be good textbooks to look through and to have as a resource as you continue moving forward. So yeah, that takes us exactly to the bottom of the hour, you guys. As always, we stay for another 15 minutes, if not longer. So I know you guys might be tired and you want to just jump off. That is perfectly fine. That is up to you. For everybody else that would like to stay and ask questions, I am here for you. Everybody that's leaving, I'll see you guys next Wednesday. We'll be doing a review, and then we'll talk about air traffic control concepts. Okay, in different ways, air traffic controllers help manage the demand of air traffic. You guys have a great night, and I appreciate all the participation. You guys take care.
Thanks, Alan.
Thank you. Hey, Brian.
Hey, there was just one thing on the profile section of the approach plate. There was a I guess down on the runway there was a label that said TCH, and then I think it said like 52 feet or something. What does that refer to?
So the TCH is the threshold crossing height. So as you're on the glide slope there and you're descending down, as you overfly the runway threshold, the beginning of the pavement, it's just telling you how high the aircraft would be over that portion of the runway.
Okay.
Yeah. So nothing really that would impact you or the dispatcher in any way, but it's more of a design and a pilot piece of information.
Gotcha. Okay. Thanks. Appreciate it.
You bet. Yeah, there's a lot of things like that we're just not going to touch on. I mean, you got to keep in mind too, we train people for months, if not years, on these concepts, as you can imagine.
Oh yeah.
We really just touch the surface, and it's tough because you got companies out there, airlines, that are asking quite difficult questions to our dispatchers that I'm sitting here going, I need to know that, but I mean, come on. They don't really need to know that, but they're asking these questions. And so we're trying to prepare you guys the best we can so that you're going in with the knowledge that they want. But I don't personally believe it's always crucial.
Right.
Right off the bat. Anyways.
Yeah. Gotcha.
So, yeah.
Thanks, man.
So good questions. Sorry, guys. I'm just trying to get over it. Like I said yesterday, a cold. But Brett or Pete, go ahead. I'm sorry.
Yeah, nothing. I was just waving by. Thanks.
Oh, hey,
Me too.
thank you, man. Yeah, my pilots out there, I know you guys are probably snoring, but I appreciate it.
No, all good. I'm trying not to talk too much because I'm getting over a cold also, so I sound like I'm getting over a cold.
Like you're getting over a cold. Yeah, I get it. I know. Yeah.
All right.
Thanks again, Pete. We'll see you on Wednesday.
Cool.
See you. Brett.
Yeah, so I'm not sure if you mentioned this because I was a little bit late to the meeting yesterday at the start, but what do you work for the FAA? What do you
So I don't work, I'm not a Fed. I don't work directly for the FAA, but I do work at the FAA Mike Monroney Aeronautical Center where they train the air traffic controllers. I was just previously one of the instructors there, teaching people how to develop, maintain, and establish these instrument approach procedures. That's what I taught. Yeah. So I've kind of gone back into my role. I really love producing and actually developing this material. So I just recently shifted roles again, and I actually decided to go back into the production world. So now I'm in this every day again, which I love. So I get to actually develop and maintain instrument approach procedures, departures, and airways.
That's really cool. Do you use a lot of like GIS programs as part of that development?
We do. We use a program called Targets, and I kind of showed some screenshots of targets in that image where we develop the flight path, and then within those boundaries, those red lines, we evaluate for obstacles. And so, yeah, it's not a CAD system, but it is a digital program that we use we use Google Earth and other technology to evaluate for obstacles around in a flight path.
That's very interesting. I have just started a couple months ago, kind of getting into that a little bit, because for my students, I was trying to work on writing my own little program that'll grade instrument approaches based on like ground, like data like for flight. To really dig into the like how the FAA nav data files are formatted and stuff, and it was a little more complicated than I thought, but it's pretty interesting stuff. That's very cool.
It is, yeah. And if you ever want to know more about it, just call me up sometime and I can kind of show you around. And I mean, you're instrument rated. I mean, you're an instructor. They're always looking for people who have that kind of background. And I mean, if you can get an aircraft dispatch certificate on top of everything else that you already have, your flying background, it's a pretty rewarding career. I'll say that. And I always give credit to my dispatch experience for the job that I have, because you have flying experience. Everybody around me at work has flying experience, or they're an air traffic controller. And here I am, just a little old dispatcher, but I'm doing, I'm staying up with them. I'm keeping up with everybody. And your dispatch certificate really covers a lot of the areas of expertise that you need to know to do the job. So,
I was so far with the studying, I've been surprised at how thorough and in-depth this is. It's been interesting. It's been fun.
Right. It's kind of crazy, huh? You wouldn't think that it would be jumping into it, especially with the experience you have. But yeah, there's quite a bit that they do expect us or would like us to know over time. So, but yeah, we're trying to talk to you guys, right, over the phone, and the pilots, they want to know, they want to be able to speak to somebody that can speak their lingo. And that's really what we're trying to do, is mold somebody into, somebody who can speak in a way that the pilots understand. And then they want to speak to somebody who understands their lingo. So that's our goal. But
well, it's very cool. And I really was very interested in the slides about the development of the minimum stuff. I didn't know all that. That was really cool.
Well, if you ever want, you can go online and Google, say, FAA 8260.3, and you can actually look at that rule book that I was talking about and just scroll through it. And it's really cool. If you look at the table of contents, you'll be able to kind of see the material that's included there. And somebody with your instrument flying background, and you already have kind of that mindset, you might enjoy seeing how a lot of this material is determined for these different segments of an approach.
Yeah, I think I will check that out, because that would be very interesting to know the why a lot more.
Mm-hmm. Yep. Yeah, you get the why, right? Like, there has to be a reason behind this nonsense, and there is. So, yeah. Well, Brett, yeah, thanks again. And
I really appreciate it.
Yeah, after class, after weeks go by and you're with a student and you have a question, I always love getting to know different people and all the different pilots, and we talk and chat and we learn with one another. So I'll make sure to give out my information next week.
Yeah, and so I don't know if I heard you mention you are located in Oklahoma City.
Yes.
Right. So I used to. I've never flown out of Oklahoma City, but I lived in Stillwater for a while and did a bunch of flying out of Stillwater.
Did you go to OSU?
Kind of miss Oklahoma. No, I was just doing a Part 61 school there in Stillwater, but I miss Oklahoma.
Oh man, Oklahoma's great. Everybody thinks, Oklahoma's trash, but no, it is a wonderful place.
Oh, I miss it. It was. I mean, I'm in Phoenix now, but we had a good time. Going up to Eskimo Joe's when we were in Stillwater.
Yeah. That's awesome. Yeah, it's a good place. We definitely enjoy it. For sure.
Cool.
Well, man.
All right, I think I'm gonna hop off, but thanks a lot.
Yeah, you're welcome, Brett. Take care, man. See ya. Hey, Lakeisha, I'm sorry. Did you have a question too? Or Siwar? All right, I guess we are good for tonight. All right, everybody take care. See ya.